Hello, I'm the Gob. In this video, I'm going to be going over my fully procedurally generated maze, level, and prop system that I created for a video game. This is all in Unity 3D. A bit about myself. I just recently finished a bachelor in computer science and a minor in games design. I've been working on this kind of procedurally generated project for maybe a year now, off and on. This project is the third iteration. The first one was approximately a year ago, lasted over winter break, took me around a month or so. And then another one began in May, and that one I think was a month or so as well. Here, you're now going to see just some quick gameplay of what it actually looks like in-game, recorded from the editor. So this video will be broken down into a few smaller sections. I'm going to try and keep the code to a minimum. Hey yo, Gob from the future now. Spoiler alert, I did not even try and keep the code to a minimum. I also figured it's kind of silly for me to try and explain the breakdown of the video, like the sections, before actually making the video. So I'm coming back and I'm going to do that properly now, and I'll like timestamp stuff as well. But the main parts, so firstly, who am I? We've already covered that. Lil GamePlay Demo. That's also covered. Then I go and I explain the cell templates and the template IDs. So this is kind of spawning the floor plan. I then explain how the cells are kind of made in the first place, so the structures, and then how the actual maze is created, so like destroying the walls and the algorithm there and what it actually does. While creating the maze, I also lay out how I make this path, so basically just making sure every single cell is accessible. This path is then used to actually spawn props randomly. So just making sure, even if we're spawning a big prop, that there'll be space for the player to get through the door. Finally, how the cells are actually instantiated and the props are instantiated, rotated, and moved, so within the world. I briefly touch on the object pool, just explaining some of the spawn points and how lights and audio sources are pooled. And finally, I explained this load player area class, which is essentially my own system that I created so that I could have some form of occlusion culling, because this is procedurally generated, so I can't use Unity's built-in system. And then an outro. I'd also like to briefly mention here, this video is pretty long, so at times I might misspeak, so take advantage of contextual clues. I think when I explain the things for the first time, I usually get it right, but I might say X instead of Z or cell instead of node sometimes. So please bear with me. If you notice anything too egregious, or you just want to let me know how I can do something better, please leave a message, and yeah, enjoy. So I'd firstly like to kind of explain, when I say matrix, what I mean. So a usual array is just one row, one line. Like this could be an array. And you have something at index 0, index 1, index 2, index 3. Here, when I say matrix, what I mean is a two-dimensional array. So that means each one has an x value, which is the first number, and a z value, which is the second number. So if I said there's something at index 1, 2, you would know that's in this square, 1, 2. Just to get that out of the way. So when I first start building the level, this is what I have: an empty matrix of integers. Each square can hold a number. In this case, I'm using something which I consider to be an ID. So -1 means it's uninitialized. There's nothing in there. These are the IDs that I'm actually using within this integer matrix at the beginning. The ID corresponds to a shape of a cell. So here 2 by 1 means 2 along the x-axis and 1 along the z-axis. And that cell's ID is 1. Same for a 1 by 2 cell and a 2 by 2 cell. Within the game itself, these are given as template cells. So here, template 1 by 1, 1 by 2, 2 by 1, etc. And its ID is its index in the array. What these template cells actually look like is, if I choose the 1 by 1, all it is a ceiling and a floor and a script which says it's a cell that has its dimensions and a little bit more information. A 1 by 2 cell here, 2 by 1. So when I create this matrix in the first place, I put -1 in every single one of these boxes, which means everything is uninitialized. Then I go through, so starting here and going up, 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 and then once I hit the top, going up, 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 etc. all the way until I get to the end. What I'm doing here is I'm choosing a random ID, a random one of these numbers, and trying to put it into the cell. As an example, let's say I'm at section 00 and I want to make a 2 by 2 cell. Its ID 3, I would put a 3 in here. Then, because it's a 2 by 2 cell, I now mark these cells with -2, which basically means they're part of something bigger. The cell at the bottom left is always going to be considered what I call the base cell, which means for this cell, this would be the base, this would be the base, this would be the base, and the 1 by 1, this would be the base cell. That is its fundamental ID, and then everything else can be calculated based on its dimensions and its base cell. I change these from -1 to -2 so that then, after I've checked all of these, when I come back here and try and add something, I know, oh, it's -2, so I can't actually add anything in this. For the same reason, if there was a cell here, its base index would be 2, 3, this would be -2, and then if I tried to add a 1 by 2 cell here, I would see, oh no, even though the base index is free, what would be part of it is already occupied. Already, I would like to make one distinction, which is the difference between a cell and a node. So here, each of these are cells. This would be a cell, this would be a cell, but each cell is comprised of nodes. So within this cell, it would have 2 nodes, and here 4 nodes. The nodes are kind of like, if you think of smaller 1 by 1 cells. So this 1 by 1 cell is also just 1 node. So if we look here, I've kind of color-coded things to make them a bit easier to see. After the first run with the integer matrix, these are kind of the cells that are split up. So a 2 by 2 here, 2 by 1 here. But what it actually looks like within the array is this. I do this because if you try and just spawn a cell or instantiate a cell and then you go on and do more math somewhere else, I believe it's inefficient. I'm not an expert on this subject, but it's how I ended up doing things. Here we have the cells themselves and their base indexes. Here you can see there's only an ID at what would be the base index for each of these cells. As a demonstration, within the editor, you don't need to pay attention to anything else quite yet, but this would be what the nodes look like. So you have this 4 by 4 grid, and this would be what the cells look like. So here, everything is split up semi-randomly, but because it's procedurally generated, if I restart it, it's a completely different layout. So, as we saw in the diagram, each of these cells, its base index, bottom left. So in this case, its base index would be where my mouse is right now. And if I select it, you'll see its name is 1, 0. That's 1 on the x-axis and 0 on the z-axis. And its position is 10, 0. This might be a bit early, but its base index corresponds to its position in the world divided by 10. So for this cell at 1, 2 is at 10, 20. So bottom to the left is its base index. Just quickly, when choosing which ID or which of the cell templates we try and spawn at any given stage, it's basically random. We choose a random one, see if it fits. If it doesn't, we try another one, etc. Some reasons why it might not fit is maybe it's trying to use 3, 3 as the base index for a 2x2 cell, but it goes out of the bounds of the matrix, so there's just not enough space. Or, like we saw before, we might be trying to spawn a cell which would overlap with a node that's already occupied by a different cell. So this is another reason why it would fail. I know I said I'd try and keep the code to a minimum, but here, so we set the integer matrix defaults. This is just where we're going through and setting everything to -1. And then here, this is where we're creating the integer matrix. So the floor layout, where we check if there is a -1 at the position x, z. If there is, we try and find a template. We get a list of all of the IDs. The list would essentially just be all of these IDs, so 0, 1, 2, ... This is because sometimes one level might have a different number of IDs. We then randomize that list. We check if it can spawn, making sure it's inside of the bounds of the matrix and making sure it doesn't overlap with a cell that's already been spawned. If that doesn't work, we remove that ID from the list and try again with another one. If it does work, then we choose the ID of that prefab and add it into the integer matrix, where at the base position x, z, that becomes the ID of the cell template, and then for the dimensions both in the x and the z, we make them -2. After we've finished creating the integer matrix, we then move on to spawning the cells. Here you can kind of ignore all of this and just come to this. So we're once again iterating through the entire integer matrix now, going from here to here to here to here, etc. Checking if the value at that position is greater than or equal to 0, which means it's an ID, aka it's the bottom left of a cell and is the base index. And if it is one of those IDs, we spawn the cell. To spawn the cell, we firstly instantiate one of the template cells. Then we update the cell's data, which involves giving it a parent and moving it. Here you can see that x and z correspond to the base index of the cell, and we're moving the cell by x times 10 and z times 10. We also rename it. We add cell data to it, which isn't very important right now, and then we set the cell's base index. When we call set base index within the cell, we firstly give the cell its base index, which corresponds to this. Here, these are how the cells actually look, and these are their base indexes. Then we set its relative indexes. Now, before I explain this, I would firstly like to establish here you have multiple arrays of structures. These were all created earlier when the cell was first instantiated, so when this line of code was executed. And all these correspond to is the walls that the cell will have later on. So they hold information like if the wall has become an entrance, which means the player can walk through it, or if it's a regular wall, so the player can't walk through it. They also each have a local and a global index. Now, when we are setting these relative indexes, that's what we're actually setting. We're setting a local and a global index for each of these walls. I would like to start off with the world indexes because they're a bit more simple to explain. But as you can see here, now these are all nodes. So this is the base cell. That's what BC means. And then these within each node correspond to the base cell. So 1 by 2, 1 by 2, because its base cell is 1 by 2. And here each wall, so within this 2 by 2 cell, you'll notice while there are numbers here and here, there's no numbers here and here. That's because there aren't walls facing inwards on the cell. And these wall world indexes, what they essentially correspond to is the node index on the other side of the wall. So here's 0, 2, 0, 2, and vice versa, 1, 2, 1, 2. These are basically pointing what's on the other side of that wall. Here it's null because it goes outside of the matrix, so there's no cell on the other side. These wall world indexes are used later on for creating the maze. Now, on the other hand, the wall local indexes, which look like this, are basically constant within a given cell template. So if I look at this 2 by 2 cell, you'll notice it has the same wall local indexes as this cell, 1 and 2, 1 and 2, 0, 2, 0, 2, etc. What these local indexes are actually doing is when you add the local index to the base index, you get the wall world index, which is this. So here it was 1, 2 as the base index, 1, -1 as the wall local index, and if you sum them, you get 2, 1, which is the node on the other side of the wall, as well as the wall's world index. The code looks a bit more complicated. I explained the wall world index first because I think it's a bit easier to wrap your head around, but for the local index, as an example, for the positive Z walls, which for this cell would correspond to these walls, which are at the maximum in the Z direction, their local index at the Z position is the dimensions of the cell in the Z direction. So here for a 2 by 2 cell in the positive Z, it's 2 and 2, which are the Z dimensions. Same for the X in the 2 by 2, whereas here in a 1 by 2 cell, the maximum here is the X of 1. Here you have -1 and -1 in the X direction for the negative X walls, because the base index is always in the bottom left. If you go one more to the left, you'll have the cells on the other side, whereas in the positive directions, you have to consider the cell's dimensions to be able to find the node corresponding to the other side. Then the X value would start from 0 and then increment, so 0 and then 1. This is once again because the base cell is in the bottom left. So here, when you want to find the node on the other side of this wall, you don't actually change the X because you're going straight up. Whereas here it's 1 because it's 1 step to the left and then 2 steps up. Now, after we've set the base index and finished updating the cell data, here this line is basically assigning the new cell that we create, the object in the game, to a position within a cell matrix, which is like the integer matrix, but instead of holding integers, it holds these cell objects. And we're assigning this new cell we've created at the base index x, z. Then we update the cell matrix. This involves assigning every node within the cell matrix the cell which we've just created. So if we go back to the int matrix, if we now consider this a cell matrix, here at the base cell, this is where the cell was actually created, and this is its base index. Now, what we're saying is if you check node 0, 1, look at node 0, 0. So at any point from now on, if for some reason I wanted to check, oh, let me see the cell at 2, 3, the matrix will basically say, yes, there is a cell at 2, 3, but then when you look at its data, you're actually just looking at the data stored in the base cell. So we're basically saying these aren't copies, there's no duplicate data, but when you try and access whatever is here or here or here, you're actually accessing what's here. So this is all this is doing. You can ignore all of this. It's a kind of edge case for the start and the end cells. But once again, I'd just like to reiterate, now we can find the node index of any node adjacent to any given cell, only using its base index, 0, 0, and the dimensions of the cell, 2, 2. Now, once we've finished spawning that cell, we go through the rest of the matrix and spawn the rest of the cells. Once cell spawning is done, we can now generate the maze. Here in this function, you can kind of ignore all of this. This is the main line we actually care about. So this maze generator script, we pass it the cell matrix, which we just saw, a Boolean matrix, which is a little bit different. Within a Boolean matrix, instead of it being any number, any one of these indexes, it's either true or false. We use this because then later on when we're generating the maze, this is usually referred to as depth first search, but we get a list of all of the possible next cells. So if we're at 0, 0, then we would have 0, 1 and 1, 0. So we can go to either of these. But when we are at 0, 0, we mark it as true. It's being visited. That means later on, we can't go back to it. So our valid neighbors here, let's say this one, 0, 1 is false, and 1, 0 is true, which means it's been visited. That means the only way we can actually go is upwards, 2, 0, 1, and as soon as we do, it goes from being false to being true. And we repeat this throughout the entire maze. So each index can either be true or false, and if it's false, that means we haven't visited it yet, so we can go to it. But if it's true, that means it's been visited, so maybe we came from 1x0 to 0, 0. So we don't want to just go back and forth, etc. That would just, basically waste time. So instead, we just mark it as true once we visited it. So we pass this Boolean matrix and then the start position of the maze, so where we want everything to start from. In our case, let's assume we're starting from 0, 0. So we pass all this information over to this maze generator, and it copies a lot of the information, or it gets pointers to it, verifies the start position, and then calls the generate maze with this start position that we just talked about. Now, once again, the position here that I'm referring to, this 0, 0, is actually the index within the matrix, and that's accessed in this manner. So here we have this cell matrix, and then the x index, comma, the z index, and now we're actually accessing the data of this cell, so we can get all of this stuff. So using these indexes, we firstly get the base cell, and then we visit it. Visiting the cell is essentially what I was just saying with the Boolean matrix, where we have its base index, for example, 0, 0, and we have the dimensions of the cell because it's a 2 by 2. So using the base index and the dimensions, we know we can now mark all of the nodes within the cell as having been visited. So at no point in the future, let's say if we're here, we won't be able to come down. So we visit the cell, and then we get a list of the cell's neighbors. This is where the whole world indexes actually come in handy, because we know the whole world indexes here are equal to the node index on the other side of said wall. So simply by getting a list of all of the whole world indexes for a cell, so for this cell it would be all of these, and I may have lied earlier when I said these were null. These are actually still a value, but it would just be, 0 in the x and then -1 in the z. But so there is actually still a whole world index there. But we return a list of every single one of these. After we get them, we firstly remove the out of bounds neighbors. These are the null values here because they are out of bounds, so we wouldn't actually be able to go there because there's nothing there. Then we remove non-existent neighbors. We can ignore this for now. Then we remove the visited neighbors. This is what I was talking about here. So at 0x0, if we got a list of the neighbors, remove the out of bounds ones, so we're not looking here, we would have both 1x0 and 0x1. Then because we know 1x0 has been visited because its value within the Boolean matrix is true, we now remove that from the list of neighbors, and the remaining neighbors we know have not been visited. This is what removing the visited neighbors looks like. We're going through the list of neighbors and then checking within the Boolean matrix if the neighbor at that position is marked as true. If it has been, then we remove it. If it's not, then it's still a neighbor. After removing the visited neighbors, there's some other stuff we don't need to mind. And then we randomize the list of neighbors because here the list would still have the positive Z neighbors first, then the positive X neighbors, etc., which wouldn't make a very fun maze because we'd always just go straight upwards. So we randomize the list, then here add bias to it. This we don't need to bother with much. But now what we have is a list of all of the neighboring nodes that are within the matrix and have not been visited. I've decided to take the one at the end of the list first. It's randomized, so in theory it wouldn't matter, but here we're removing from the end of the list each time, so there is a good reason for it. But we select this chosen neighbor. Here the vector2 int is basically, it's similar to a normal integer, but where a normal integer could have just one number like 1, 2, 3, the vector2 integer has two numbers within it. And you can access these by doing the variable name .x and the variable name .y. So this chosen neighbor corresponds to the wall world index within the cell or the node on the other side of that wall. So here, let's say I choose 1, 2 as my chosen neighbor, which corresponds to this as well. I then pass into this destroy walls function the cell that I'm currently at, which would be this, the cell that I'm going to based on the chosen neighbor, which in our case would be this, as well as the chosen neighbor itself, which is 1, 2. We pass the chosen neighbor as well because while in our case it worked out because the chosen neighbor is the base cell, if let's say I passed in 2, 2, so going up from this cell, when I access 2, 2 within the cell matrix, what it does, as we saw before, is it actually just accesses this data. So just based on this cell, we don't actually know which wall it was accessed from. Like in a case where a cell shares two walls with another cell, if we were just to pass the cells themselves without the wall world index, we wouldn't know which wall to actually break. So that's why we pass that. And we pass all of this to a destroy walls function. So once again, we have the cell that we're currently at, the next cell that we're going to, and the wall world index. We then find the wall's local index by subtracting the wall world index from our current cell's base index. So here, in this case, it's more simple, 1, 2 minus 0, 0, still 1, 2, but you'll see here with the wall world index, the wall local index is the same. So this is the number we're finding with that subtraction. We then make a copy of the wall world index. This copy is a bit useless, so you can ignore that. You can also ignore all of this. But we find the wall's local index relative to the current cell. Then we call destroy wall within the current cell, passing its local index as a reference. What this destroy wall function within the shell script actually does is it uses the local index and the fact that some of the values are predetermined to find if it's a wall on the positive Z side. So here a wall on the negative z side, etc. Because we know if the z index is equal to its z dimensions, it must be a positive z wall. Similarly, if the z position is -1, it must be a negative z wall. For the x, if the x position is the x dimension, so here 2 and 2, it must be positive x. And if the x, I just realized I was on the world indexes, but because we're in the bottom left, it doesn't matter too much. But if the x position is -1, then we must be on a negative x wall. So using that information, it can find the array of wall datas that we briefly touched on before that needs to have a wall destroyed within it, and then just calls destroy wall, which within the wall data, all it does is mark that a wall has been destroyed and then change the status of the wall. Here we have wall destroyed and entrance, because later on, as we'll see, each cell has its own walls and entrances, so the wall surrounding the entrance, but there's only one door frame that's shared between them. Then, based on which wall was destroyed, we actually modify the local index that was passed as a reference. This is because here, in this example, where it's a positive z wall, so this wall, if we decrease the wall's local index by 1 in the z-axis, so here 1, 2 minus 0, 1, which is just decreasing it by 1 in the z-axis, we get 1, 1, which, and this is kind of retrospectively silly, but now if you add 1, 1 to the base index of the cell, you get this node index, and you need that node index because now we basically call the exact same function again, but swapping next cell and current cell. So now we're trying to break the wall going this way because each cell has its own wall. So we switch the two of them, and if we use the updated wall local index here plus the current cell's base index, here's 0, 0 as the base index and 1, 1 as the updated wall's local index, we still get 1, 1, but that corresponds to the wall world index to this node, which is also stored as the wall world index of the wall opposite the one we just destroyed. When destroying these walls, the local index is updated based on the direction we're going. So if we're going upwards, the local index is decreased. If we're going downwards, the local index in the Z is increased. Same for the X, but solely using the X part. We're using the local indexes because these values, so when it's a positive X or negative X, here when we destroy a positive X wall, we're using the Z value of the vector 2 to find the index within the list of positive X walls, because once again it goes 0 here, 1 here, so that's why we're actually converting back to local indexes. But just from looking at the world indexes, I know it seems kind of silly, and I think there's probably a better way to do it now. We're essentially getting this by decreasing this value by 1. Okay, now that we've destroyed the walls both relative to the current and here relative to the next cell, we call another function which is update level specific data. Here what we're passing is this temp value, which was just a copy of the first cell's wall world index, and the updated wall local index plus the base index. This is once again just the wall world index relative to the next cell. So what we're passing is this and this. Then within update level specific data, we call another function. We don't actually care about this one too much, but that's update prop nodes, and we're passing in current cell and next cell, this and this. Now, before getting in to update prop nodes, I feel like I have to go back and explain something I kind of brushed over earlier. So here in this generate maze function, we created a prop node matrix. So what this is it's a 3-dimensional matrix of this type, prop node status, which all that is it has three possible types for each index, so it can either be none, it can either be path, or it can either be prop. So if we go back to the initial matrix, each of these indexes now can either be nothing, it can be considered part of the path, or it can be considered a prop. But the main difference is, unlike previously, where let's say this is a cell, the red wall is the negative x, blue wall is the positive z, it's just one high. This one is actually 4 by 4 by 4. So we're splitting up every single cell into these smaller cubes, which, if I only show the ones directly adjacent, looks kind of like this. So there's 4 along the x-axis, 4 along the z-axis, and 4 up the y-axis. And this is the same for every type of cell. So a 2 by 1 or a 2 by 2, this is actually what's going on here. If I were to just run it real quick, I know it's kind of egregious to look at, but this is what it really is. Every single cell is just broken up into smaller and smaller parts. And each of these values, each of those smaller white squares, can either be considered none, path, or prop. When it's created the first time, all of them are considered none. So here, when we actually create the prop node matrix, we're using the dimensions of the level in the x direction times 4, which is the number of cubes per cell. Then the dimensions of the floor or the level in the z times 4, and then just 4 in the y, because I haven't actually needed to make anything bigger than 4 yet, so I just chose to leave it like that. So just for a comparison, if this was our integer matrix before, where we had 0, 1, 2, no, on the z, 0, 1, 2 on the x, what it now looks like is this, where we have here, this should be z, but we still have the 0, 1, 2, but we also have 0, 1, 2, 3. Every single one of these is just broken up to 4, and same here. Each index that we were looking at before now has 4 smaller indexes. This is also just shown in 2 dimensions because I don't know how to draw in 3 without it being really messy. Here, I just want to maybe briefly explain the purpose of this. So the prop node matrix is what we're going to try and do is we're going to create a path between every single cell to make sure every single one is accessible by the player. And then we're going to use that to kind of create a border where we're not allowed to spawn props and we can only spawn props around it. Now, I'm not saying that we're going to make sure the player can visit every single node, because in this case here, you see the path in theory would go through these 2 doorways. So the player could get through here and over to this side, but it only needs half of this cell. That means we could spawn something massive here and the player wouldn't be able to access it, but that's okay because it's not actually preventing the player from getting around. So that's kind of the purpose of the path that we're creating now. So we call this update prop nodes passing in the current cell and the next cell, aka the 2 wall world indexes. I'm going to be just explaining this with the diagrams because the code is super duper messy. What it essentially does is if we take over these 2 wall world indexes as current and next, so we have current at 1, 1, which I'll just mark, with that, and then next, which is 1, 2, which is right here. So we firstly want to make sure that the doorway cannot be blocked. So we're trying to locate between these 2 cells where the doorway is, which will turn out to be these 4 prop nodes, if you will. These are the nodes we're trying to get. We can see that because we know, oh, we're clearly just going directly up and the doorway is always in the middle. So it's obvious in this case. But to actually find that just using these, we firstly check which value is changing. Is it in the x, first value, or is it in the z, the second value? Here, in our case, the second value is changing, the z. That means we're going upwards or downwards because this is constant, so we're going up. If the x was changing, then we'd be going to the right, and the z would be constant. I would also like to mention, currently where the x's are placed within the nodes, these are kind of like, if you think about before we had a whole cell and then we had a base cell in the bottom left corner. Now here we have a whole node and sort of a base node in the bottom corner. That's because here we have the whole world indexes, which when multiplied by 4 will give you a prop node index. So here for the current, it would clearly be 4, 4, and that ends up being here 4 and 4. Same thing for the next, it would end up being 4, 8, which is 4 in the X, 8 in the Z. So once again, we're just getting the bottom left. We don't necessarily know the direction we're going in or where the path should be, because the ideal path, just to draw it out, would be all the way from here to here, and then in the middle, it being higher because there's a doorway. So we don't want props spawning higher up, but the doorway is only really visible in 3 dimensions. So we have these kind of node base indexes, but now once we've compared the current and the next and we found out we're going directly upwards, we add an offset in the X by 1. So the offset would be 1 in the X, 0 in the Z, which would essentially push these X's over by 1. We're offsetting them right here. This is because we don't actually want the path to be directly along the wall because the doorway is in the center. So here we found this offset. Then, because we are just trying to get this doorway, I'll highlight it. We are just trying to get these 4 prop nodes. We figure out, in this case, which one is lower. So we know the X value is the same. So here, I would also just like to mention this offset is in prop nodes, so 0, 1, 2, blah, blah, blah. But the current and the next are still in just regular nodes, so the bigger numbers. So now that we've figured out we're going directly upwards and we've offset in the X direction correctly, you can see the next one is actually already within the green. That's because we're going directly up. The X offset was actually all we really needed to find that value. However, the current node is still way off. So to actually change that, what we do is we compare which one is smaller in the Z values, and because it is the current, we increase it by 3. We add an offset for the current by 3 in the Z direction because we know we're going up, which essentially moves the current all the way up to here. Just to quickly reiterate, I don't want to spend too much time on this, but if let's say we started again and we had a current at 2, 2, we would find its kind of node base index by multiplying by 4, which is 8, 8 and 8, 8. And if we were, let's say, going to this cell at 3, 2, so next is 3, 2, which we once again multiply by 4 to get the prop node index. We see it's at 12, 8, so 8 here and 12 here. I'll rewrite this quickly. So 8, 8 and 12, 8. Here we see because the Z value isn't changing, it's remaining at 8, we must be going along the x-axis, which we are. So because we're going along the x-axis, instead of what we did before where we added an offset in the x to shift it to the right, we would add an offset in the z to shift it up. So we shifted up and both of these are +1 in the z-axis. So 8, 9 and 12, 9. I'll highlight it again, but this is where the doorway is supposed to be. And ideally what we want is we want both of these 2 base indexes to be in the bottom left of their respective node. So here, because we're moving along the x-axis, what we ideally want is x here and x here, whereas before, because we were moving along the z-axis, we want them to be one on top of each other. So we want them to be aligned in the direction that the entrance is going, to the left or to the bottom. But because, once again, the x is still here, and we actually don't know if the next one is in the correct position or if the current one is in the correct position, we compare the x value, because we're moving along the x-axis, see whichever one is smaller, and here, because the 8 is smaller than 12, we then add an offset to the current by 3, which is the number of prop nodes per larger node minus 1. So here, plus 4 minus 1 is just 11. 11, 9. And now we know we're in the correct position. So here, I'm going to temporarily remove the offset just so that this is more easily explained. So 11, 8 and 12, 8. So they're back below where the entrance actually is, and they're both below where we actually want them to be to make sure we're going in the right direction. So here upwards, we do it twice for both the current and the next, but we do the current plus the offset and the current plus the offset times 2. Same thing for the next. Here I'll remove where they were previously. So here current plus the offset is 11, 8 plus 0, 1. So 11, 9 here. Then current plus offset times 2, 11, 8 plus 2 times 0, 1, 0, 2, which is just 11, 10. So here 11, 10. Same thing for the next plus the offset. Next is 12, 8 plus 1, and then plus times 2. This method works because it's the exact same in this case, where if I were to rewrite out the current and the next in terms of the prop node indexes, we had the 4, 4 for current down here and 4, 8 for the next up here. And then because we saw after comparing them, because they're moving along the z-axis, the current z value was less than the next z value, we added this current offset. So now it's 4, 7. So because here we notice we're moving along the z-axis, there's only an offset in the x to move it over away from the wall. So we do the current plus 1 times the offset. So 1 plus 4, 5, and 7. So here, and then the same thing but the offset times 2. Same thing for the next, so with the offset 5, 8, and then offset times 2, 6, 8. So that's kind of how it's actually working just to find the doorways. This is what the actual code looks like. We have a current offset, a next offset, and a normal offset. Here, the normal offset is increased by 1 in the z component. We're moving left to right if the z value is not changing, which is the same as saying the x value is changing, so they're not equal. So that offset gets added, then we compare, see which one's smaller. Whichever one is smaller in the value that is changing. So we assign that to the cubes per cell at -1. Here, this is just because we're going upwards. In the third dimension, we're considering the y-axis as well. So this is how it actually looks like then when we're just iterating through the prop node matrix. Everything got a bit messy, and this is why I use diagrams, because this code is barely readable. But this is once again just for the doorways. So here briefly, if you ignore kind of everything else, this 4 by 4 square is what we just found. We were saying we were in maybe this room when we went into this room. So we found this 4 by 4 square and marked each of the nodes as path, and it goes upwards so that it covers the doorway so that later on we don't try and accidentally spawn something on top of this doorway. So they're all set as path. That is what their node status is. We then also add a prop node path. So here we were just doing the doorways, now we actually need to connect the cells. So here I've just changed it from wireframe to solid color, but if what before we were finding these 4 cubes to make the doorway and make it slightly elevated, now what we're trying to do is connect from this node that's part of this entire cell, this node, we're trying to connect it to this node that's part of a bigger cell. So that's all we're trying to do. We're trying to create this green square all the way to this green square. And these are also too high. Just quickly with the wireframes here, we're trying to connect these 4 to these 4 is all we're doing. So to add this prop node path, we kind of do a similar thing. We check if the current cell's x and the next cell's x are equal, which would mean it's like the case where we had this node and this node being connected because the x is not changing, so we're going up or down. Then we compare the z values once again. Here we're checking which one is smaller. So let's say maybe we have 2 doorways, so this going to this, and this going to this, we firstly find the prop node index versus the regular node indexes like these. So we multiply their node indexes by 4 to get the prop node index. This is what we're actually trying to find for these two nodes. And then for the blue and yellow ones, we're trying to find this. And we're just trying to mark all of this as a path. Then we compare, we see here, is the current cell's x the same as the next cell's x? So in the case of here, these two nodes, they are the same. So that instantly tells us we're either going up or down. In this case, they're not the same, but the z are the same, so that means we're going left or right. So here in the case where they are the same, which means we're going upwards or downwards, we check once again, we find which one is lower down relative to the other. So in the case of the current cell being lower than the next cell, here we're checking their z values. So just like here, if this is current and this is next, we see, oh, the current cell is lower down because its z value is smaller. So because the current cell is lower than the next cell, we start. Here, what we're really trying to do is find the bottom left of whatever it is. So because the current cell is lower than the next cell, we'll start within the current cell. Because we know we're going up or down, because the x values are the same, the x component within the prop nodes matrix is very easy to find. All we do is choose the current cell's x value, multiply it by the cubes per cell as we did before, and then add 1 and add 2 separately. This is similar to what we were doing with the offset before, but because we know, firstly, their x values are the same, going up or down, we can simply find this and this by adding 1 to it or adding 2. Here, both of these are duplicated because we're also increasing the y value here, but the actual path, let me just draw it out real quick, that we're trying to create here is this. I should have done this sooner probably. So here, because we know going up or down in the z-axis, the x is the same, we can just do +1 or +2 to the x component for both the current and the next to get the right x values for the entire path. Then, because the x values are taken care of, we find the z values. These will begin in the current cell, but once again, offset by 1. So the current cell's prop node value in the z dimension +1, which was the current cell's prop node value in the z dimension 4 +1, so 5, which is here. Now, because we saw the x was constant, so the offset would be constant, so we can just kind of hard code that. And then we increased it by 1 in the z dimension because the current cell was lower. Where we're actually at right now is here and here, which is in the green box, and then we iterate all the way through, only changing the z value. So just going up, 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 all the way until the z value is equal to the next cell's prop node index in the z value +3, which was 4,8, and so that is the next cell's prop node value in the z, and then +3, 11. So we go all the way until the z value is equal to 11, but we don't include it. Here you'll see it's a smaller than, not a smaller than or equal to. So once this z value is equal to 11, we stop. So this doesn't actually get visited. Now this is for the case where we're going upwards, so current cell is lower than next cell, and the current cell's x is the same as the next cell's x. A similar thing happens if we're going directly downwards, so the next cell's z value is lower than the current cell's z value, but instead we start in the next cell and finish in the current cell. And it's also basically the exact same thing if we were going left or right, but here instead we're iterating over the x value and the z value is kind of constant and just predictable, and the x is what's changing. And so we execute this, updating the prop nodes and adding a path between the two nodes that just got destroyed once every time the walls are destroyed. So every time when we're generating the maze recursively that we destroy the walls, we're adding these pathways between. straight away. And now, after we finish destroying these walls, we call the exact same function here, but we pass in the neighbor's x and the neighbor's y that we just went to. So if like before this was the start cell and we chose the wall world index 1, 2 to go upwards into this cell, we now call the exact same function, but instead like at the start where we passed in 0, 0, now we pass in 1, 2, and it just repeats the exact same function for however many cells there are, like could be hundreds. And after we call this function recursively, we once again remove the visited neighbors and then try and do the exact same thing, destroy the walls on our next neighbor. This is because here when we started at 0, 0, all our possible neighbors included 0, 2, 1, 2, which we ended up choosing, 2, 1, and 2, 0. So now we went to 1, 2, so we went up. So obviously this got removed from the list, but we still have all of these. Then within 1, 2, this one is like, okay, I'm here, and then it can choose, maybe it goes here. And so now this one gets visited, but this one doesn't have any neighbors it can go to. This has already been visited, and it came from here, so it's also been visited. So this function basically gets to the point right here where it literally has 0 neighbors and just quits. And so then we backtrack, going back into this cell, and then from this cell, let's say now we go down. So this cell gets visited, but this other cell still thinks it might be a neighbor, still thinks 2, 1 might be a neighbor, even though it's been visited because nothing's told it to remove it as a neighbor. And so now within this cell, we're like, okay, I'll check which neighbors have been visited, and it was these ones. So we redo it, remove them, and now visit this cell. I don't know if that makes sense. I don't know if it's super necessary, but whatever. So we continue, we recursively call that until there's nothing left to check, at which point we call another function on maze generated complete, which does some other stuff, but mainly it connects the prop node paths. So here we once again iterate over the entire cell matrix. When we connect paths, the case that we're actually trying to solve here is like this, where right now I know if I were to spawn props wherever I want, there's a chance that it might, create some massive thing right here. And now maybe this is my only exit out of this cell, so I can go here, but I won't be able to get to the rest of the maze. So I clearly need something else that's going to come in and be like, oh, you're over here and you're over here. Let me just fix you guys up like that. Or in another case, maybe these two got connected as well. Then it's like, oh, let me just connect you. Or in some cases, like connect like this. I don't think it would do that. We'll ignore that. But so we just need something to connect these. And that's what this function does. So we go through the whole thing and try and connect the paths. To connect the paths, here we're getting the positive Z paths. So paths along this wall, and then positive X, negative, But so we're getting each of the paths and then updating them with this offset. So we get the positive Z paths, which all they're actually returning is the wall world indexes of all the positive Z walls. So here, if we got the positive Z paths for this cell, it would just be returning 0, 2, and 1, 2. So now, because we have those wall world indexes, which we know correspond to the node on the other side of the wall, for the positive Z, all we do is decrease each one by 1 in the Z axis. So here, 1 in the Z axis would mean it goes to 1, 1, and we're basically getting the nodes within the cell. So here, decrease the Z by 1, or, if we got this, because it's a positive X path, we simply add -1 in the X and 0 in the Z to it, to then get 3, 2, minus 1, 0 is just 2, 2, so the node index within the same cell. But when we get these paths from the wall, we only return the wall world indexes of walls that have been, quote, destroyed. That means the destroy wall was called, which means they were used to create a path from one cell to the next. So here, the only one that would actually come out is this. So what that would mean in this case, for example, we're not returning these walls. We're only returning this, and this, because there's a path leading out from it. Then using those wall world indexes and modifying them a bit, we're basically getting from this wall, for example, we're getting 1, 3, which is this node. From this wall, we're getting this node, and from this wall, we're getting this node. We're doing that because maybe if, let's say, this wall was actually another path and these two were connected, we don't want duplicates. So we only really care about the node, not the wall itself, because we're connecting things within a cell. We're no longer connecting them to outer cells. And we only return the ones with nodes that are broken, because we don't actually care about this, because for all we know, there could be a massive, boulder in this corner, and it doesn't matter because the player doesn't have to go by that corner. The player can just get around it. So we get all of those wall world indexes that have a path, and then we get the nodes within the cell that have a path leading out from them. And then we make that list distinct just so that we're not doing it from multiple things. We then reorder the paths, which is really just checking, let's say, if we had all of these paths and we got the nodes from them. So here, 1, 3, 1, 2, and 2, 2. When we create this list, there's a chance that it'll be ordered like this, starting 1, 2, then 1, 3, and then 2, 2. So that would mean if we try and connect the paths, we'd have to go like, oh, here, and then like somehow get over here. So we don't want that to happen. So what we do is we check if the distance between the first one and the second one, these two, is greater than the distance from the first one and the third one. And if it is, so here, this distance versus this distance, then we actually just swap these two. Okay, upon further review, I may mess up here, but it hasn't shown in the game, so I don't know, but it's worked so far. But this is just for reordering them anyway, whatever. But it works and it reorders them. But so that's just reordering the paths. It doesn't even matter that much. I don't know why you're still talking about it because I don't care. Now for the actual thing, so checking if there are disconnected paths. Here we need at least 2 paths. And we check for disconnected paths. So this would be, let's say, if there are only actually 2 paths leading into this cell. Here these would be disconnected because you can't like draw a straight line to either of them. There's no way. Both their x and z values are different. So here this cell would be 1, 3, and this one 2, 2. So they're both different, so they'd be considered disconnected. So very complicated. To connect these, what we do is we create a new fake node that pretends to have a path, and we just take one of their x position and the other one's z position. So here it could be either 1, 2, which would be this, or 2, 3, which would be this. And we just say, hey, Baba Booey, there's a new path over here, and this one needs to be connected, so please connect to it. And we just choose one of them. And so now once the disconnected paths have been connected, or they're now basically considered, there's more nodes, and so they can all be connected by straight lines, we call for the entire length of the paths. We call add prop node path for all of these individual nodes that need to be connected, firstly starting with the first and the second index in the list. So here it's kind of like we just said, here there's now 1, 2 is a new thing, so 1, 2 here. And we call the function that we had before, the add prop node path. So this function is the exact same as what we were just doing before, but there it was between 2 different cells, but still just connecting 2 adjacent nodes. So we had the current in the bottom left, the next, bottom left up here or whatever, and then we had the offset in the x because the x values were the same, which mean they're going up or down, and then, iterating through all of that. It's the exact same function. Instead of passing 2 nodes in 2 different cells, we're just passing 2 nodes in the same cell. So it would be like passing the green and blue. It's the 1, 2, and then 2, 2, and it would do the exact same thing add the offset, move it up, whatever, and just connect these two. And so all of that combined here, once again, red is an entrance, blue is just a cell wall. But with all of that combined, we end up moving from something like this to something like this. Here, everything is clumped together, but you can see from this cell, we have this doorway. It doesn't work so well here because the doorways are just fully open planes, but it connects here. It connects within the same cell, moves over, adding the doorways where they have to be. This space could have a big prop, or this space, and it's just a good path because the player itself can fit between these, so we can kind of spawn props anywhere else. So once again, if I were to enable the empty cells and then draw it as a wireframe with a lower opacity, this is kind of what it was before. So here, all of these white cubes that you can faintly see are every single prop node, and then in green is the path, and it goes up one higher at the doorways, and then it's just too high everywhere else, only in the center of the room. I can reload this as well, and it's a similar thing, but a completely different floor layout, this time just including the path, and it's a straight line basically. But if I increase the dimensions of the maze here from 4 to, let's say, 16 by 16, you'll see you start to get some more complex paths, so not necessarily always super linear. This is where we had to create a fake node. Actually, this might be an example of where my program went wrong, because it should have just connected these two. Or in some cases, you know, like connect like this. I don't think it would do that. We'll ignore that. Okay, upon further review, I may mess up here, but it hasn't shown in the game. So, okay, maybe I am the problem. It's a feature. From a kind of higher up standpoint, you can see just from the starting position in the bottom left, every single cell is accessible as long as you don't block this path. And it's kind of the minimum space required for every cell to be accessible. Not every node, like you have big things here, nodes the path doesn't cross. But yeah, I'll just reload this again quickly. And it's a completely different layout, different rooms, different room variations. So now that we've called connect prop node paths and all of the prop nodes have been connected with paths, we invoke this event, which our level subscribed to earlier before it called for the maze generator to generate the maze. And so what that does is when that event is invoked, it's basically calling this function, and this is where we move on to actually spawning props. So we are assigning the cells, and we add a prop spawner to the level game object, and then tell it to assign the props. Now, what I'd firstly like to do is explain how the props are made, the different types of props, and the information that comes along with that. So firstly, if I select one of these levels, let's say the hospital, it has this cell data that we kind of ignored earlier. So this cell data is basically a data structure that stores all of the props. This is how it looks. It also has the wall prefabs and the entrance prefabs and some audio source stuff, but that's not important right now. What we're going to be looking at is the different types of props. So this is where they are input. Here on the cell data scriptable object, once again ignoring all of that stuff, we have the lists of props. So the fundamental type of prop here is just prop data. This is used for the regular props, but all it is a prop, the dimensions of said prop, the chances it will spawn. So 100 is it will always spawn, 0 it will never spawn, and then if it can spawn against the wall, and if this prop should be used. So this is just an easy way to toggle them on or off. So here I'll start off with the regular props and kind of show how they're made. So this is the cell, once again, split up into these smaller prop nodes. And now if I were to enable this prop, here you can see the chair is placed within this 1 by 1 by 1 cube, this kind of prop cube, and it's in the back left corner. But its pivot is still in the center. So you have this prop script, and then it just references its children, not a specific component. So here its only child is this chair, but this is just 1 by 1 by 1 because it only takes up this one cube. However, this, on the other hand, is a 1 by 1 by 2 prop because here, once again, x is going this way, z is going upwards. So it's a 1 by 1 by 2 prop, but the pivot for this prop is still in the back left corner. And here it just has all of its children references just quickly within the prop script. Here it is a literal list of game objects called children, and then later on it extrapolates information about the children, like if they have renderers, colliders, rigid bodies, etc. But so I place this prop into the world. I try and make sure it fits within a certain amount of cubes, and then I add a new game object to make as the parent of that, and I make sure that one is not rotated at all, not scaled at all, and has its position at 0, 0, 0, so the back left here. And here we have a 3 by 2 by 1 prop. Here it's 3 along the x-axis, 2 along the y-axis, so going up, and then 1. So these are how they're initially made. Once again, the pivot is always in the back left corner of the prop, and it's not rotated. And so as we saw within the prop data script here, when I add a new one, like these medic curtains right here, I simply drag the prop into this section, add the dimensions, so 3 by 2 by 1, the chances of it to spawn, and to use the prop. Here I don't want it to spawn directly against the wall, so I leave that blank. This is how a prop is created. If I wanted to add a new one, it would just be moving it into the world, finding the kind of minimum space it can occupy, and then adding a parent, making sure the parent isn't rotated or scaled, and has its pivot at 0, 0. Okay, now that that's out of the way, so here back in the script, we assign cell props here, and that's basically calling a function within the prop spawner to assign props. The prop spawner is added to the level game object at runtime, and basically all of its data here just references the levels data. So when we call assign props, we firstly try and get the level on which this script was added to then be able to reference the levels data. And if we can get that reference, we then iterate through the entire cell matrix once again and call this function should add props, which is just saying check that props haven't already been added to the cell and check that this cell isn't part of a list of cells that have been chosen to not have props. So in our case, mainly the start and the end cell. If this passes, so we should add props, we call this add props function. Here we're initially only passing in the x and the z value, and then we use that to find the cell within the cell matrix. So here cell matrix xz, and then by finding that cell in the matrix we can access all of its prop data. As we saw before, all of those lists are being stored within a scriptable object that is initially placed on the level, and then a reference to it is passed to the cell when the cell is instantiated. So here I'm firstly going to be focusing on the regular props because this is kind of where my documentation and code literacy fizzled a bit, so it gets quite hectic. But here we create lists of all of the different types of props that we saw within the cell data scriptable object. The regular props aren't included. I'll explain that later. So here I'm going to skip over some of these. Here, getting the prop matrix borders is we pass in the cell, so the x and the z component, and then a reference to this array of integers. And we use this to find the borders of said cell. So here all this get prop from cell function does is it returns the number we pass times the number of cubes per cell, so in our case 4. And to find the positive z border, we have to pass in the cell's z component plus the dimensions of that cell. And then after finding that, we do -1, because here what we're essentially finding is, once again, we're using this base cell base index plus the dimensions, so in our case 2, and then we're multiplying that by the number of cubes per cell. So here it's 4, so we got 0 plus dimensions 2 times the cubes per cell, which is 4. But what we end up getting is the first cube in the cell above it, so we just do -1 to get the inclusive maximum Z value for this cell. For the X and the Z values, it's much easier. We're just multiplying the index by the cubes per cell. So if we were in this cell, it's just 2 times 4, 8, and we get the bottom corner, and 1 times 4, 4, we get the bottom left corner. So the negative borders are much easier to find. Now here, once again, just kind of ignoring the stuff above, we create a list for the regular props, and then we call this function getRegularProps, where we're passing a reference to this empty list here, and then the list of regular props that we stored in our scriptable object, this list of regular props. So right here, this is the list we're passing over, and when we call getRegularProps, we also pass in the cell as a vector2 int, which is just a container for its X and Z value. GetRegularProps. We iterate through the list of prop datas that we got from the scriptable object, check that the actual prop object isn't null, check that we're supposed to use the prop, so this bool is toggled on, and we check that the prop isn't bigger than the cell, so we pass here the cell's index and the prop dimensions, which are just stored right here in the list. And all this function does is it instantly calls another function in which we pass the dimensions of the cell, so the X dimensions, the Y dimensions, and the Z dimensions times cubes per cell. So when we call the function for, let's say, this cell, what we pass in is its dimensions, so 1 in the X and 2 in the Z. But when the function is executed, what it actually has is just, instead of a 1x2 cell, it's a 4x8 cell. So that's all that kind of middleman function is doing. But what we're just doing is making sure that the dimensions of the prop are smaller than the dimensions of the cell. So if it's a big prop that has X dimensions of 5, it wouldn't be able to spawn in this 1x1 cell, so we instantly discard it, meaning we return false, which means this fails and it's not added to the list of regular props that will actually try and spawn. Here we also just get a random number from 0 to 100. If that number is greater than the prop's chances to spawn, then we won't add it to the list either. This just means if the chances to spawn are 100, then it'll never be bigger, so it'll always spawn, and if the prop's chances to spawn are 0, then this number will always be larger, so this will always fail and it'll never spawn. But all we're really doing is updating this once empty list of props, and these are the kind of candidates that will try and spawn in the cell afterwards. So after this is done executing, we have a list of props that fit within our cell and have been chosen. We check that that list has at least one prop and that this flag is set, so we're trying to spawn regular props in this level. So that would be here, just this flag being checked or not checked. If this was not checked, then this would fail and we wouldn't spawn them. So that's how I can kind of turn them on or off easily. But let's say it all goes through, we now add regular props. Here we're passing in the list of regular props that were acceptable for this particular cell, the prop matrix borders, so the borders of the cell in terms of the prop cubes, and then this is just whether or not the prop is considered a floor prop, which means it can spawn in the path. And finally, if it can spawn against the wall, which would just mean if, let's say, we had a 1x1 prop in this cell, instead of it being able to spawn like here or, here, it can only spawn in the center, so just not against the wall. So we call add regular props. Here, this you can kind of ignore. It's just me trying to find out how many props I want to spawn within this cell. And then for however many number of props I decide I want to spawn, everything within this loop gets executed that many times. So firstly, we check if there are no more props in the list, we quit. But if there's more than one prop in the list, we randomize the list. This is just because if a prop fails to spawn, then it isn't actually removed from the list because there's a chance it still would be able to spawn somewhere else. So we just randomize the list again, and maybe it will be able to spawn the second time it tries, but only if it is actually successful in spawning is it removed from the list. So what makes it successful at spawning? We call this canSpawnRegularProp function, passing in the first prop within the list, so of regular prop datas, the prop matrix borders, so the edges of the cell, whether or not it's a floor prop, and whether or not it can spawn against the wall. Here, this might have actually been a mistake, but we redo the check if it can spawn, so give it a second try to fail, and we initialize a rotation value and then a ROT. This is just an integer where 0 corresponds to no rotation, 1 is 90 degrees, 2 is 180 degrees, and 3 is 270 degrees or negative 90. So here we have a base offset and relative dimensions. This is needed because unlike previously where we were creating the cells, where the base index was in the bottom left, now the base prop node index, if you will, is actually in the top left. This means that unlike before, where just using the base index and the dimensions of the cell, we could get the indexes of every single node within the cell. So here, up 1, to the right 1, up here, just using base index and the dimensions. However, now it would more so look like the base index is in the top left, but the dimensions are the same. This is why we have a base offset. That would basically just say this is actually the base position, even though the base index is placed up here, and the relative dimensions serve a similar role. I think it'll be more easily explained as we go on. Firstly, we do check if the prop that we're looking at is a 1x1 and it's a floor prop, so it doesn't have a collider. We can spin it basically any rotation. If not, then we choose a random rotation. So this is using the ROT as an index 0 to 4, but not including 4. And then the actual rotation is just 90 times the ROT. So firstly, you can kind of ignore this for a sec, but in the case where we're placing the prop on the positive Z, this is how it would actually kind of look. You have the pivot in the top left, and then the dimensions go down and to the right. We built it facing the positive Z. Once again, the x-axis goes along this way, but the positive Z walls and the negative Z walls are parallel to the x-axis. It's like this because they are placed along the maximum Z value within the cell. But within the prop node matrix, there's a few problems if we just go at it like this. Here, the prop we're looking at, dimensions would be 3 by 2 because it's 3 in the x-axis and 2 in the z-axis. However, its base index is at 1,7. So unlike before, to find, let's say, the bottom left corner, where we just used the base index because the base index was in the bottom left corner, and then added the dimensions to it, -1, to find the top right corner, we actually need to offset the base index to use the dimensions as we did before. Here, I've kind of just laid out a little bit of the math. So the pivot is at 1,7 and the base dimensions are at 3, 2. Now you'll see here for calculating the x values is actually pretty similar to what we were doing before. This is because it is still all the way to the left on the x. So before we had the bottom left corner, now it's the top left corner, but the x moves left and right. So the x is mostly unaffected by this for now. So to find the left edge, we can still just use the x component of the pivot. So here that would just be 1. And to find the right edge, we would just do the pivot plus the x dimensions -1. This is just the exact same as before. So just 3 plus 1 minus 1, so 3. And we do in fact get the edges of the prop, so 1 and 3. However, for the Z component, it's a little bit more complicated because we're starting from the top instead of the bottom. It's basically just switched. Where to find the top, we now just use the pivot's Z component. So here 7, which is the top. And to find the bottom, now instead of doing plus the dimensions -1, we do minus the dimensions +1. So we're going backwards, which is just the position 7 minus the Z dimensions 2 plus 1, so 6. And once again, we get 6. So these are the actual borders. The bottom left would be 1,6 right here, and the top right would be 3,7, so just here. And we need to find these to actually figure out the border of the prop based on its rotation. This one is a bit more simple because we built it as positive Z. This would be the actual base index of the prop on which you could just use the dimensions like we did before. But so here, when we calculated this, this is actually the offset. And so this prop placed on the positive Z, this is what the kind of formula for its offset would be, but in our case here, because we know the dimensions in the Z is 2, we can just instantly put it as 0, -1. So that means if we want to find the bottom left corner, or like the base position, we just add this to the pivot. and we get the bottom left corner. This only works for props placed on the positive Z wall, and this corresponds to this line of code where we get the base offset. Here the relative dimensions haven't actually been changed from the props dimensions. So this is the case where there's no rotation. Now, as we move on to the positive X, however, where we've rotated it 90 degrees, so it went from here to over here, it's a little bit more complicated because firstly, the dimensions no longer actually even correspond to the right X and the Z. So here, when we're finding the left edge, which would mean this wall, that is the negative X, we still use the pivot's X value, however, we use the Z dimensions because these have basically been switched, as now where it was before like this, 3 in the X, 2 in the Z, it's now 2 in the X and 3 in the Z. However, in the actual code, instead of messing around with the Z for the X and all of that, I just instantly create relative dimensions that we saw earlier, which are just the opposite, so 2, 3. Here, this is what the code is doing. So this is case 1, which is 90 times 1, so we've rotated 90 degrees, instantly creating relative dimensions that are just the opposite of the props X and the Z dimensions. Then now to find the right edge is extremely easy because it's just the pivot's X value. Here, 7, we're on the right edge. Then also for the top, pivot's Z because we're top right, so 6 right here. However, to find the left edge and the bottom edge are what's more complicated now. This is where we add these kind of offsets. So here, the left offset would be 1 minus the Z dimensions, or 1 minus the relative dimensions X component, which in our case would be equal to 1 minus 2, which is just negative 1. And then the Z offset would be 1 minus the X dimensions, or 1 minus the relative Z dimensions, so just 1 minus dimensions dot X, which is just 1 minus 3, which is just negative 2. Because if we start at the pivot, we know we're actually at 7 minus 1, so 6, 6 minus 2, so 4 at the bottom left, and here 6 and 4. This is the actual base position, and we can find that using the offset. So this is what this code is doing here, firstly switching the relative dimensions so that now the relative dimensions X is equal to the props initial dimensions dot Z, and then the base offset for the X is just 1 minus the relative dimensions X, and base offset for Z, 1 minus relative dimensions for Z. So placing on the negative X is once again a more simple one because our pivot is in the bottom corner. So as before, where our pivot was all the way to the left, that means that we only had to offset the Z component because we are already all the way to the left. Now, however, because we're all the way at the bottom, we can assume we'll only actually need to offset it in the X. So here, we don't actually need to change the base dimensions, they're good. And our pivot is at 6, 0, 6 in the X, 0. Yep. The right edge is our pivot's X because we've now rotated from this to this, where pivot was here, now it's here, now it's here. So the X value of it will already be the right edge right here, and the Z value will be the bottom because it's already in the bottom right. Now to find the left edge, this is where we assumed we might need the offset, and that's exactly this part. So 1 minus the X dimensions, and that's just the pivot's X plus this. So 6 plus 1, 7, minus the X dimensions, which are 3. So 7 minus 3, 4. And we get exactly the left edge, or the negative X value, and this is going to be the offset, so we can assume it'll just be 1 minus 3, negative 2 as the X offset. So the offset would actually look like negative 2 and 0. Then finally, just to find the top, we do the pivot's Z value. So in this case, 0 plus the dimensions minus 1. So same old bread and butter. 0 plus the Z dimensions 2, and then minus 1. This will be the top border and the positive Z. But within the code, this is exactly it. The base offset in the X component is just 1 minus the relative dimensions X component, which hasn't changed from just being the props dimensions. And finally, for placing it on the negative Z, here I wrote negative 90 degree rotation, but it's also just 270. Our base dimensions once again become relative dimensions at 2, 3. Our pivot is now bottom left. So basically what we've wanted since the start, we have the pivot as the base index. So in theory, just using these relative dimensions 2, 3, we should be able to find everything. There shouldn't actually be any offsets to be used, but we still have to get the right edge and all of the other edges. The right edge is just the pivots x, 0, plus the z dimensions. So here the z dimensions correspond to the base dimensions. So for the relative dimensions, it would actually just be the x again. So 0 plus 2 minus 1, 1. So our right edge will be at 1, which is what we see. The left edge is just the pivots x, which is at 0. Perfect. The top is the pivots z, so 1 right here, plus the x dimensions or the relative z dimensions, 3, which is 1 plus 3, 4, minus 1 again, 4 minus 1, 3. We get the positive z edge. I hope this is kind of explained for the rotation so far, but this within the code, all we're doing here is switching the relative dimensions and the prop's original dimensions, so the x relative dimension becomes the prop's z dimension and z becomes x. Now, using those z dimensions and x dimensions, we check if the prop can spawn on the wall, which means, like in all of our cases here, it's always been against the wall. However, if let's say we didn't want it to spawn on the wall, what those would really do is it would just kind of pretend that all of the edge parts aren't inside of the node or the cell, so you can only spawn starting from 1 and up to 6. So let's say here in the case where it can spawn on the wall, we choose a random position, a random prop node within the cell between here the prop matrix borders -x, which let's say we're looking at this cell. The -x would be 4, just right here. Once again, it's inclusive. So between that and the positive x here, minus the relative dimensions x plus 2. So this may kind of seem like magic numbers at first, but to explain, it's basically here the positive x would be 11, and thinking back to the previous prop, which was 3x2, so we have the 11 minus the relative dimensions x, which here is 3, plus 2, which is 10. This is because if we think back to the prop where it started like this, when we are trying to spawn it, when we're looking for a node, what we're finding still is a kind of bottom left, and then we use the offset and the relative dimensions to figure out how to place the prop afterwards. But what we are still finding is the bottom left. So in theory, we don't even want to try and place the prop here because we know it'll exit all the way out of the cell. That's why we're getting this 10 as the maximum value, but it's not what you think where this prop is allowed to spawn at the 10, because here this random.range in Unity, that means it can spawn starting from the first value. So the prop could spawn at 4, the minimum, right here, but it wouldn't be able to spawn at the maximum value. So it really is just between 4 and up to 9 inclusively. These are the valid values, but it won't try and spawn here because we already know that it would exit out of it. And because we have the relative rotation already, if let's say it was already switched, so the prop was rotated so it would actually look like this, we already swapped the dimensions earlier into the relative dimensions. So in this case, what we would actually be doing is 11 minus the 2 and then plus 2 to get 11 again. But so that's why we were creating the relative dimensions earlier. We're not thinking in terms of offsets or anything yet. We're just finding a valid bottom left corner for the prop to spawn in. So for example, let's say here we chose this to spawn a 2x1 prop. The prop itself might actually have its base index in the top right after being rotated once or twice, but we kind of figure that out afterwards. Here we're just making sure that the space is free and within the cell. And then we do the exact same thing for the Z borders, but here doing relative Z dimensions plus 2. So if you think of the X here as red, we actually have within the cell, we're not allowed to try and place anything to the right of this line. If we still have a 2x3, that doesn't mean that this entire part of the prop can't be in here, you know, and then have the X protruding right here. That's still completely okay. It's just if we try and put something here, it'll go out. And then for the Z, because we know it's too high, the Z blocks any attempt at spawning above this line. So once again, it would still be able to spawn like this, but it just won't try and put the bottom left corner here. And in the case if it can't spawn on the wall, all we're doing is we're increasing the negative X and Z borders by 1 and decreasing the positive X and Z borders by 1 as well. So it would only actually be able to spawn within here if it wasn't allowed to spawn on the wall. And the base position's Y value is always just set to 0 at first. After we have this pseudo random position, so anywhere within this square, we check if we can spawn the prop, passing in its base position, which is the random thing we just found here, and its relative dimensions. So within can spawn prop, we firstly create a list of acceptable cubes for the thing to spawn in. So this is just if it's a floor prop, we actually want it to be able to spawn in the path. So instead of just checking if there's already a prop somewhere, we actually can, in certain cases, allow it to also just spawn in a path. We start from the base position. So let's say, I don't know, I chose here to try and spawn it. So the bottom left of the prop would be here, which is at 812. So this is the base position that we found, and its relative dimensions are still 3, 2. So starting from x at the base position, which is just 8, going all the way until x at the base position plus its relative dimensions, so 8 plus 3, 11. Once again, this is smaller than, so it will actually stop at 10. And then the same for the z, starting from the z position to z plus the relative dimensions. So here from 12 to 14. So once again, exclusive. If we want the inclusive bounds, it would actually be from 8, 12 to 10, 13. And then we're also checking the y values for all of the props' y dimensions, but we're iterating through this 3-dimensional array and just checking if any of these cubes have a status that's not none, which means it's either a path or a prop. If the status is not none, then we return false. We're doing this because earlier I might have added another prop that was just this big, and so therefore these cubes, these prop node cubes, will all have already been set to prop, and that means that this cannot spawn here because it would collide with another prop. The other reason why it would fail is if it collides with the path. So if this door was open and we had a path right here, and then I tried to spawn the prop right here, it would see, oh no, these two cubes are part of the path, so I'm not going to let you spawn there. But even if that fails, there is still another chance for the prop to spawn. This only really applies if it didn't collide with another prop, but it collided with the path. And that is what this can shift path function does. We're passing it in a similar thing, so the base position, which was this 8 and 12 in our case, the relative dimensions, which were 3 and 2, they didn't actually change, and the prop matrix borders. So here it would be negative z8, positive z15, negative x4, positive x11. That's what we're passing in here. And once again, this is only executed if this can spawn prop fails, which means we collided with a prop or a path. I'll talk about this a little bit more shortly. It is kind of an edge case most of the time. But assuming that we were able to spawn this prop, so this is an OR, which means if this function succeeds, we'll instantly go in. If this does work, we call update prop matrix, passing in the base position and the base position plus the relative dimensions. And all this does is it starts at the base position, so 8, 12, and then goes all the way to the base position plus the relative dimensions, which is, as we saw, inclusively 10, 13. So it just goes through everything and marks everything as a prop, so that in the future, if we try and spawn another one and it collides, we won't get overlapping ones. After that, we add a prop prefab to our cell. So this is the actual cell that we're adding it to. In this case, the cell would have the base index 1, 2, and we get that by dividing the base position by 4. And because it's integer division, even if we had 5, 15 as the position, 5 divided by 4 in integer division is just 1, and 15 divided by 4 is just 3. So we're not getting the base index here, but we are getting a node index 1, 3, which, as we saw before, when we look into the cell matrix, all this actually does is show us this cell's data, and we tell that cell to add a prop prefab. Passing the prop itself, then we get the spawn position, which is the base position minus the base offset. All this is finding out where the pivot would be relative to the bottom left corner. So in the case where we were placing on the negative z, here the base offset was always 0. We only changed the dimensions. So that means the base position, which was the bottom left and is always the bottom left of the prop, is equal to the pivot position, 0, 1. However, here in the case where we place it on the negative x, the base position would still be here at 4, 0. However, to get the pivot, we do the base position in the corner minus the offset, which is minus negative 2, 0. So 4 plus 2 6, 0, and that is actually the pivot position 6, 0. So for the positive x, where we had the two offsets, the base position would be here 6, 4, and then the offset we found was -1, -2, so minus -1 and minus -2 respectively, which just ends up being 7, 6, which is the pivot position. Earlier when we found the base position, we were just using that and the relative dimensions to go through the matrix of prop nodes. However, now we need to find out where to actually place the prop in the world, so we need to find where actually to place that prop relative to its pivot. So that's what we're actually finding as the spawn position. That's what we're getting here, and that's actually where we tell it to spawn later on. We also just find its base position, so the bottom left, regardless of how many times it's been rotated. We pass its relative dimensions, which are only changed if it's rotated either 90 degrees, which means they got swapped, or -90 degrees, which also means they got swapped. And finally, we pass the rotation and return true, meaning that this prop will be removed from the list. So within cell, this add prop prefab, what we do is we copy over a lot of the data into this prop info, which is different from the prop data that we had before. This prop info has the prop object itself, so the prefab we're going to spawn, the prop's position, which is like before the bottom left of the prop, regardless of where its pivot is. The relative position, this is where the pivot is. So here we have the prop position, bottom left, and then the relative position in the actual pivot, the relative dimensions, so these once again are only different if it was rotated, and the rotation in degrees. So we copy over the prop prefab into this prop info, the prop's position. So here the prop position and the relative position are actually more so local positions. So here earlier when we had the prop's position, we said it was 8, 12, 8, 12. This is its kind of world position. The local position that we're finding here is relative to this cell. So to find its relative position, we just do 8, 12 minus the cell's base index times 4, which converts it into prop nodes. So the base index turns into 4, 8, and 8, 12 minus 4, 8 ends up being 4, 4, which here, if you just consider this as index 0, 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4, we get its relative position within the cell. So we do that. It's the position minus 4 times the base index. Same thing for the Z and the relative position using its actual spawn position. So this is where the pivot will be. Copy over the relative dimensions and then add the prop to this list of props, which we'll later on use just to iterate through and instantiate all the props at the same time. So before I get ahead of myself, I'd like to revisit this can shift path function. So to kind of briefly explain what this is actually trying to accomplish is, let's say this situation occurred. So earlier when we were checking for places to randomly spawn the prop, we were only finding the kind of bounds within the cell in which we could place a, in this case, 2x2 prop, but we weren't actually considering the path. This is only checked later. But in a scenario like this one, where the prop does actually block the path, there's this kind of edge case where the prop will essentially try, if there's space, to push the path around itself like this, and in doing so, return this area to nothing so that the prop can spawn. So to do so, we pass in the prop's base position, so the bottom left, its relative dimensions, and the prop matrix borders, so the positive x and z and negative x and z borders of the cell that we're in, and we start. So firstly, we get the cell's base index, and then using that, we get the dimensions of the cell in terms of prop nodes, so just 4 times the cell's x and z dimensions. Then if the x and z dimensions are 1, we basically say it's impossible because, like in this case, there's just not enough space to actually move the path. We also check if the prop's relative dimensions in the x are greater than the cell's x dimensions minus 2. This is because, let's say in this scenario here, where there's a path going through this 2x1 cell, if we have a prop that's, let's say, 2x3, we'll never be able to fit the path around it because the path always has to be at least 2 wide to ensure the player can get through. So we would have to make the path actually look like this, which is going out of the cell, so we ignore it. In which case we return false again and don't even continue. We then get the prop edges. So this is what we were finding when we did all of this, getting the bottom left and the bottom right, left edge, right edge, bottom edge, top edge. So that's what we're computing again here. Then we add every single prop node that this prop would take up in theory to a list, which was defined right up here. So in our case, this would include 6, 8, 6, 9, 7, 8, 7, 9. So just all of these individual nodes, we add them to this list. We then create a few more lists. We then find the entrances, paths, and path cells. Here, all these four functions are actually doing is exactly what we saw earlier when we were looking at the maze generator, where we were connecting the paths. So what we're actually finding here is what we found here when we connected the paths. In the case that we're currently looking at, the path cells are actually the path nodes. So this and this. If there's a path leading out up here, then another path cell would be this. But it's just every single node within the cell that has a path leading out of it. But if there's only one element within this list, so if we were looking at this cell, that would be the case, then we say no straight away because there's not really anywhere to shift it, and I don't know, it would make for very much change. So now, once we have a list of all of the nodes that contain a path, we go through and we add the prop nodes that are either an entrance or a path. So we're starting from the bottom left of the cell, -x, -z, and going to the top right, +x, +z, checking every single prop node and seeing if it's either a path, which would mean its node status is equal to path, or if it's an entrance, in which the node status would also be set to path. But because we saw earlier in the editor, the path nodes are the only ones that actually go too high to cover the door frame, so we only check the nodes that are too high. Whereas for the normal path, they're at 0, and we're adding just a vector 2 because we don't actually care about the y component of the path. We just want to know if each individual prop node is a path or if it's part of an entrance. Then we go through the list of entrances and check if the distance between said entrance and any given corner of the node, so here -x, -z, -x, +z, +x, -z, +x, -z, we check if the distance between that entrance and any corner of the prop is smaller than 2. So here the entrances would be set as this node and this node. So for 9 and 410, we would also be looking at 11.9 and 11.10, and we check if any given corner, so this, or this, if it was a larger node, like here, then the corners would just be this, and this, but we compare the distance, so 4,9 to 6,9, and we would see if this distance is smaller than 2, and we just go through and check this with every single corner and every single entrance node. If the distance is smaller than 2, then we stop, because that would be like here, if the prop was actually trying to spawn, something there, 5.8, 5.9, then it wouldn't allow it because the entrance would be forced to go like this around it, and here it would only be one wide, so the player might not be able to fit through. So that's why we make sure the prop isn't too close to the entrance and make sure it doesn't block it. If that all works out, we now actually need to find which direction we want to push. Right now, all we actually know is the part of the prop is overlapping with the path and that we're not blocking the entrance. So we get a list of directions. These are all just +z, +x, -z, -x, and we try and add every single possible direction that we could push the path in. So to get those directions, we call potential direction to push path, passing in the edges of the prop and the prop matrix borders, so the edges of the cell. These being the edges of the prop, and the edges of the cell are just this. So to actually find the possible directions in which we could push the path, initially at least, is we just make sure that the distance between the prop's borders and the edges of the cell is greater than 1. So what that looks like is for the +z, if we wanted to check if we could push in that direction, at least initially, we say, okay, +z here, 15, minus the prop's +z, which is 9, which turns out to be 6, but we're actually just checking if that's greater than 2. We're doing this because, let's say in this case, if we tried to spawn a prop here, the -x border of the prop would be 9, and the -x border of the cell is 8, so there just wouldn't be 2 squares to push. That's one reason. Or in another case, maybe we spawn a prop in the middle of a cell, then we want to make sure that the path is shifted upwards like this, and it doesn't try and shift it downwards like this. So we're just getting all of those. In our case, it should return +z because there's all that space, -x because there are still 2 cubes available, and +x. So as of right now, we don't actually know that the path is just going through a straight line and we're coming in at the bottom. We just know that we're blocking it, so we don't know where to push it yet. So we just get this list of potential directions. If that list is empty, then we return. We then randomize the list, and we try and find every single prop node that's in the path versus out of the path. So here the prop nodes were found earlier, where we just went through the X and the Z of the prop from the base index and just got every single node that's part of the bigger prop. So here each of these would be prop nodes, and the top two would be considered in the path because they overlap with the path, and the bottom two are out of the path. So that's all this is doing. After getting that, here we're just trying to find if we're actually able to push the path in certain directions. So as we saw before, the prop nodes in the path are 6, 9, and 7, 9, so these two, and the ones out of the path, 6, 8, 7, 8, these two. And the directions to push path that we saw were valid were the positive Z, positive X, and negative Z. Negative X failed because the negative X border of the prop is too close to the negative X border of the cell. So we try and find the nodes that, if the path were to be shifted, would now become paths that are not currently paths. So what we're trying to find here is these nodes, but we don't actually know the direction to go in yet. So these new path nodes, we add a range of vector 2's, which would just be their indexes, and that range is returned from this function, which is get new path nodes. We pass it the direction we want to push it in, and the list of in-path and out-path nodes respectively. So here, the get new path nodes, initially, all it does is gets an offset. The offset starting at 0, 0. If we're going in the positive Z direction, we increase the Z value for the offset by 2 and the X value by 1. If we're going in the positive X, then we increase the X value by 2, the Z value by 1. So here, what we're actually kind of trying to find is the bounds of the new path. So if we're going positive Z, like in this case, we do Z offset increased by 2 because we're colliding here. So we have to go up by 2, and then the X by 1 because if we just left it like this and didn't have these two as path nodes, then there's a chance the player wouldn't be able to fit through this because it's only one wide. So the X value also gets increased by 1 to kind of get these bounds. And then for the negative Z, if we're going in the opposite direction, the offset in the Z would be -2, but the offset in the X would still be 1. This is because if, let's say, we were placing it here and it was legal, we'd be just going down by 2. After getting these offsets based on the direction we're trying to push it in, we call get new path nodes again. But now we're passing in the offset, the in-path nodes, and the out-path nodes. And here, the other thing that this is doing is it's splitting up the offset, so into the main offset and into the secondary offset. So here, as we saw before, in the positive Z direction, the Z component is 2 and the X component is 1. So this, we split it into the main and the secondary, so that would just be the main offset with 0, 2, and then the secondary offset with 1, 0. We then iterate through all of the nodes which are in the path. So here, these two, 6, 9, 7, 9. Temporarily, we can ignore this line. We're also iterating from -1 to 1, so -1, 0, and 1. This will be explained shortly, but we're trying to add a new path node. So this is a node that would be part of the new path. And what we're adding in this is the node that was within the path plus the main offset. So the node within the path here, let's say 6, 9, plus the main offset, so 0, 2, plus the secondary offset times j. So this is where this comes in, because we are also checking to the left. So starting from here, if we didn't have this line, we would just be checking this node right now. However, by having the j, which goes from -1 to 1, we firstly check here where it's the secondary offset times -1, so plus -1, 0, which is 5, 11, which turns out to be exactly this node here, 11 and 5. So we've successfully found this node to the left of the prop, and we're just checking that that is also free. And then afterwards we do the same thing but times 0, so this is just 0, 0, meaning instead of 5, 11, it's 6, 11, which corresponds to this node. And then finally, in the last time, we do the secondary offset times 1, so just the regular secondary offset, which ends up being 7, 11, which is right here, so 7 and 11. So for each of the nodes that are in the path, we're actually checking all 3 of the nodes that would be pushed just because it could just be a 1x1 prop. So we would want to check all of these to make sure that they're free, because once again, if we only did this and there's a prop right here, this is just a 1x1 gap. So we don't know if the player would actually be able to get through it. So that's why we're actually iterating through the J here. And we add that new path node to this list, and the index becomes the end of the list. The index is just so that we know which node we were just looking at. And then here straight away we check if out of path, the list of nodes that are part of the prop but aren't interfering with the path contains this new path node. So this would be the case if, let's say, we had this as a prop, then we would still be trying to push the path in the positive Z because there's enough space for the path to go, and we have no reason not to try yet. When here we try and shift this node up, we would find, oh, this is actually just part of the same prop, so we wouldn't be able to push it there. So if that's not the case, that means we're pushing it in a maybe right direction. We now check if the prop node at that index is something other than none. This would be the case if we're trying to shift it in the positive X, which we saw was actually a possibility. Here, when we try and shift it to the right, we would get this node right here, and we'd see, oh no, we're just pushing the path into the path. We're not actually creating a new one, so we cannot be pushing it in the positive X. And for that matter, it's the same thing for the negative X here, because the node we'd be pushing it into is already a path, so that means we're not creating a new path. Another reason for this is we might have actually already just spawned another prop in this area. We're not going to try and backtrack, it's just no, you're not going to be allowed to shift the path because something's already there. Here, this code actually seems a little bit redundant now, but what we're checking is firstly if there are nodes out of the path. So these two nodes, we check if they are closer to the new path node than the in path node that we're looking at. So we're checking if this is closer to this than this. This is because, unlike before where we had a larger node, there is a chance that we put a 4x4 here and tried to shift it in the positive Z. So because these are the in path nodes, we're just going up by 2 like here, and we'd be checking this and this. But what this actually is just catching is that, oh no, we're pushing it up and we're like splitting the path, so this will still be inaccessible, and then this will be too thin, and we're actually pushing it behind us, so this would be closer to that than this one. We also have up here this list of potentially bad nodes. We're not actually using the new path nodes with the index as we were before. What we're actually using is this temporary value we created earlier. This one is essentially the same as the new path nodes, but its main offset is divided by 2. This means what we're actually looking at isn't the new path node itself, but the node directly between the new path node and the prop node. So here, when we're adding into the potentially bad nodes, we're only adding them if the node status of that prop node isn't path. So here, because all of these would be considered potentially bad nodes, we're ignoring them because they're already path. However, in the case we saw before, where they're not equal to path. So firstly, in this case, where our prop is actually blocking the entire path, so 2x2, we would not only be checking here and here, but also here and here. When we check at this node, we'd be checking here, here, and here, but we would also be checking at this node, which would be here, here, and here. So now these would get added as well to the list of new path nodes. So at the end, after all of that is executed, we just go through all of the potentially bad nodes and make sure that the new path nodes contains them. If the new path node does not contain them, then we say no, we will not be able to shift the path because there was maybe something blocking it or another reason. But here, what we're returning is all of the new nodes that should be considered path. So we would hopefully just be returning a list including these nodes, so 5, 11, 6, 11, 7, 11, and 8, 11. And this is a success. We would get back to the new path nodes here and return the same stuff. If it failed, then we would try the next direction. However, in our case here, it worked. So we have this list of new path nodes, and if that's greater than 0, so the path is actually getting moved, we firstly remove the old paths, which is just going through the list of in-path nodes that we saw earlier, so these two nodes, and it just marks them as none, their status, 0 and 1 high, once again, because it's 3D. After that, we add the new paths to the prop matrix. So here, just the list of new path nodes that we got returned from the function, and just mark them all as path, once again at 0 and 1, and return true. This is all to say, even if sometimes the prop does overlap slightly with the path, it can still actually shift the path. And just as a visual, so this is what everything looks like just spawning the regular nodes. You still have it going slightly higher up on the door frames. Right here, this is how the path shifting works. It just goes up and down, and it's one of those cases. It's really kind of rare, but a friend of mine was like, maybe you should do this so that you're not just constantly running in a straight line. This is what all of that extra stuff, the first path itself was fine. It's cool. Also here, the red squares represent the regular props. I'm doing all the exact same stuff, I'm just not actually instantiating the props at the end. That's why they're all empty. If they weren't all empty, it would look something like this. Here, I could actually even disable the prop outlines. And right here, you just have a wheelchair that or no, just a regular chair that spawned, and they shifted the path around it. So we're just making sure that the player can get from this side of the room to this side. Right here, shifts the path, it's just a bed, that kind of thing. And so that's kind of regular props. Just to kind of briefly explain some of the other types, there's also wall props. These are essentially a regular prop, but they can only spawn against the wall, and they have a minimum and maximum height. They can only spawn within these cells. So if we go to here, this could just as easily be a wall prop where its back is against this wall, and its pivot is in the top left. That means that no matter what, it always has to be against a wall. So the pivot rotates so that its back is against the wall. There's also floor props, which are the exact same data structure as regular props, but these can just ignore the path entirely. They don't even have to shift it because they don't have a collider. Then there's per unit props. These are just pretty different because they spawn in every single node of every single cell. So here, if you think of my red dot as a per unit prop, it would literally just spawn everywhere, either in the dead center or you can kind of offset it. And this could be like maybe a ceiling lamp or a certain fan, or just something that you want in every single cell, maybe even something on the floor, like a drain at the bottom, every single node, I mean. Then finally there's cell props. These are just massive props that would occupy an entire cell. So if I come back to my prop visualizer, a per cell prop example would be this. So it just goes along the entire length of a cell. So this would usually just spawn in a 2x2 cell. It has a little bit more data. It has the cell's dimensions that it has to spawn in. So this one, once again, it can be rotated, i.e. if I create a prop that's only for a 1x2 cell, it'll also spawn in a 2x1 cell. They generally have big dimensions, but they can also have an offset. So here, it will always spawn in a constant manner. So just like this, if once again, these were all a per cell prop, they would only ever spawn right here, right here, right here, right here, and in the exact same way. So there's no randomness to these. They're spawning in a specific place within the cell. The only difference is the rotation. And so because I wouldn't want the window just to be up against a wall like this, I add an offset. So here it's in the Z direction, because when it actually spawns, what I want it to do is instead of going there, it would start there and then go 1, 2, 3 prop nodes forwards, and then that's where it's actually spawning. But it's built with its pivot in the back corner, so that's why we actually need the offset. One other thing for the per cell prop is it can actually be marked as creating a path. This is an example of one that creates a path. So here, if I disable the prop visualizer, there's a door that's created within it. So it'll once again spawn only in a 2x2 cell. However, if it is marked as creating a path, as is the case right here, it creates a path. It is marked as being able to create a path because I know no matter which rotation it spawns in, I will still be able to get to any wall within the cell, but because it does take up a large part of the cell and it will override the nodes marked as path, I don't allow regular props to spawn because they might actually still block this entrance. So that is why here earlier there's getting the cell props, and then only here do we add the regular props. This is because I firstly want to check if we do add a per cell prop, and if we do, whether or not it creates a path. And then finally, we also have interactable props. These are once again basically the exact same as regular props, but the player can pick them up. So I wanted to be able to handle them separately and give them their own logic. So here as an example, I'm going to spawn everything. This individual level has all of the props, and now we can actually come through and see, okay, this is a per cell prop, and it takes up most of this cell. It's 8 by 1 by 3. So 8 in the X, 1 in the Y, and 3 in the Z. Or here, massive prop, and I'm okay with spawning it because even though it blocks off this entire side of the cell, the path doesn't actually interfere with it, so it's okay. It can just keep going, and I'm okay with blocking that off. And because it's not creating its own path, I can then spawn regular props on this side, and even a wall prop. I'll quickly disable the visualization, or maybe I'll make it wireframe. No. But so here, this is a wall prop, and that is its base pivot, and it's been rotated and moved to make sure it's in the right place. These would be regular props. This mug is an interactable prop. Here, these cabinets, for example, you might assume that they're a regular prop, but they're actually also a wall prop. That's because you wouldn't usually just see a cabinet in the middle of the room. So the wall props do actually include ones that aren't necessarily floating on the wall, but they just need at least one face facing the wall. Here, once again, we have the path being shifted. This is okay because I know that there will be enough space for the player to get around. Here we have the medical curtains from earlier. Again, these ones are marked as not being allowed to be placed against the wall. So throughout the entire level, whenever they did get spawned, they're never against a wall. The red squares that you see floating, these are the per cell props. I recently just added functions so that they don't necessarily always spawn, so there's a bit of randomness to it. This is just because lighting is so expensive, and pretending like there's only one in every couple of rooms maybe makes it a bit more interesting, but mainly just to save on cost. Here the paths have been connected, and you might be thinking, how can this be? It's not shifting the path. This is a floor prop, so it just doesn't have a collider. The player can just walk over it, so I don't actually mind if it blocks the path. And you'll see the start and the end cells don't have props, and they'll also always be 2 by 2. But if I restart quickly, here, this is an example of a per cell prop breaking the path. So you see there's path coming in here, goes up there, and then there's a prop blocking it. In this cell, now that this per cell prop has been spawned and I know it creates its own path, I no longer spawn regular props. These crutches are a wall prop because they're tiny, but yes, so this is the case in which the regular props wouldn't be spawned, because even though here it seems, oh, the path is just going straight through the door, it's fine. I don't actually know where that door is. It could have spawned along in this direction. It could have spawned like this, and so then the door is here, or even like this, in which case the door is over here. So just because I don't actually know where the door is anymore, I don't spawn regular props. So after the prop spawner has gone through the entire list of props, checked if it should add props, and then added them, the level is called to instantiate the cells. This is where the walls and the props are actually created. So once again, we iterate through every single node within the matrix, and if the integer matrix's value is greater than 0, which means it's the base index, then we call instantiate cell on the cell at that position within the cell matrix. So here, when we call instantiate cell, we first call instantiate walls. All this does is it calls instantiate walls for the positive Z walls, positive X walls, negative Z walls, and negative X walls, also passing in a direction, and that's not really used. So here, let's pretend we're calling it with the positive Z walls. So we're passing in this array of wall datas. Now, as of right now, the only things that the wall datas actually have should be from when we set their local index, their world index, and then also whether or not the wall was destroyed, which would have occurred when destroy wall was called. So that was from the maze generator, we called destroy walls with the wall's local index. Then now within cell, we found the correct wall we wanted to destroy, and then called destroy wall for that wall data, and this wall destroyed was updated. However, now I need to mention about this add entrance. We need to add this because when we actually destroy the wall, we're not completely removing it from the cell. We're just saying instead of spawning a normal wall, like this for example, what we actually want to spawn is an entrance wall, like this. However, because these are just planes and they only have one face, we also need a door frame to kind of hide this. This door frame is considered the entrance prop. So within the cell data scriptable object, it is kept directly below the entrance and looks like this. It's just a simple doorway. This one also has a spawn point, which we'll see the purpose for later. But because we only want one of the two cells on either side of this door frame to spawn it, that is why we pass in this add entrance bool. So when we call this function from the maze generator the first time, this repeat bool is set to true. We also then assign add entrance to the repeat. So when this is called the first time, we're passing in true, which means within destroy wall, add entrance is considered true, which we then pass to the specific wall data we want to destroy. And we also pass within the specific cell data element of that array, the add entrance, which we then use to choose if we want the wall status to be entrance or just simply wall destroyed. So this is deciding whether or not the entrance wall will spawn a door frame. And then here, because we're calling it recursively, so we're only calling this destroy walls a second time if repeat is true. When we do call it the second time, we just pass in false. So when instantiate walls is actually called, all these wall data would usually have is a local index, a world index, whether or not the wall has been destroyed, and if so, whether or not it should add an entrance. So firstly, we just do a few checks to make sure everything is in order and that there's a wall to be spawned. Then we iterate through the list of wall datas and we begin laying out the variables which will store firstly the position of the wall and the rotation of the wall. We then create this local wall prefab variable and assign it to the wall data's wall prefab. This in theory should be null because we haven't actually set it. Here we check if it is not equal to null. This is just for what I call trans walls or transition walls, and these are the walls which lead out of a level and connect it to the next one. Here we're not going to focus on this, we're just going to go to the next case where this wall prefab is equal to null, and we check firstly if the wall has been destroyed. If it has not been destroyed, which means the maze generator never actually went through that wall, we assign the wall prefab to the cell data's wall prefab, which for the hospital level would just be this wall prefab here. We update its name, set the wall's X rotation to the wall prefab's X rotation. This is because the wall is just a vertical plane, which means it should actually spawn like this, but by changing the X rotation to -90, we get this wall that's facing towards the player in the Z direction. So we only copy over this X rotation. Earlier we also define an offset. This is because like here, when we actually build the walls, we're not building them at 0, 0, 0, X, Y, Z. I add 4.5 to the Z, which means when we actually create the cell, the center of the cell will be at 0 at this X, if you can see it, and then the walls will all be offset by 4.5 in each direction. Here it's also 4.5 because we don't want the walls to be exactly next to each other because they're planes. This means each wall actually has a small amount of space between the one and the other side. This is mainly because sometimes light can leak through the wall going below it or to the sides, which is just copied over here by getting the local Z position of this wall prefab before it's been instantiated. We also pass over the wall's Y position. This is once again because a normal plane would spawn at 0, 0, 0 on the floor, so we shift it up, but this is a constant number, so we can just already copy it over here because it's never going to be changed. I'm now going to temporarily move on and explain how this case would actually be carried out, where the wall was not destroyed when the maze was being generated, and then return afterwards and explain what would happen if the wall was destroyed. So here, similar to the case earlier, where we were looking at the wall's local index to find firstly which direction it pointed in, positive Z, negative Z, etc. For finding the positive Z, we were comparing the Z component of its local index to the Z dimensions of the cell. If it was true, then it was a positive Z wall. However, if the Z component of the local index was equal to -1, that meant it was a negative Z wall. The same was true for the local X index. Also quickly, I believe I mentioned this before, but if the positive Z walls are along this axis, then within the array of wall data, this wall would be indexed at 0, and then this wall would be indexed at 1. You can see this here if you look in the editor. This wall is positive Z0, this wall is positive Z1. Then if I turn to the right, this wall is positive X0, this wall is positive X1, and behind this wall, negative Z0, this wall negative Z1, and finally this wall negative X0, this wall negative X1. So altogether, if I just grab the 0 index walls, it would look like this. So each of them are aligned with the base index. Here, this is the base index, so the positive and negative Z are directly above and below it, and the positive and negative X are directly to the sides of it. So here, as we're iterating through the array, if we were looking at the positive Z, the first wall here at index 0 has its X position set to 0 and its Z position set to 15. whereas the positive Z1 wall, which would be the second element in the wall data array, has its position as x10 and z14.5. So here for the positive and negative z at the index 0, both of their x values are 0. They haven't been moved to the right or left at all. And same for the positive and negative x at 0, both of their z values are 0. They have not been moved at all along the z dimension. All this to say is we can actually use their index within the array to find part of their position, because as before, the cell's base index was equal to its position within the world. So here 2, 4 at 20, 40. The same is true for the walls, however only along one axis, and this is using their index. So for the case of the positive z walls, we found that their local index was equal to the z dimensions of the cell. We can find its z position regardless of its index, because as here with the positive x walls, they're both the same, 14.5, and we find this position by doing the dimensions of the cell minus 1 times 10 and then plus the offset. Here in a 2 by 2, it would be 2 minus 1 times 10, so 10 plus 4.5, the initial z position of the prefab when it was made. And for the x position, it's just its index within the array times 10, so here it's at 0, and here it's at 10. Now, if I were to quickly reload the scene using a lot more cells of a different variety, you can see within this 3 by 2 cell that the positive z walls both have the exact same z position value, and the positive z wall all the way to the right is now at 20 in the x position, because this was 0 times 10, 1 times 10, 2 times 10. So that's how the actual position of the wall is found, solely based on its local index. We then rename the wall with the wall's direction, its index within the list. We also set the wall's y rotation based on the direction. So here with the positive z, because they were built facing towards the player in the positive z, so this wall would be placed at the maximum z value of the cell, which is why this is its base position. Its rotation would be 0. However, if it was in the negative z, which meant its local index's z component was -1, its wall rotation in the y would be 180. For positive x, it would be 90, and for negative x, it would be -90. The other thing is for the walls that are placed along a negative axis, so the negative x or negative z, here for the negative z, its wall's z position is just the negative offset. This is because the cell's actual position is in this bottom left corner, so everything within it, all of the wall's positions are relative to this bottom left corner. So here if we take the negative z walls, all of their z positions are just 4.5 because it's relative to the center of the cell, its pivot, which is right here. It's also worth mentioning that this occurs regardless of if it was destroyed or not, or if it has an entrance. The only real difference here would be the wall's x rotation, the initial offset, and the wall's y position, because this is all entirely based on how it was built the first time. So here for the hospital wall versus the entrance wall, here the entrance wall is actually set at 5, and then the children, the rail and the wall, are both set at -0.5, which in total turns out to still be 4.5 like before. So that's why this is just being done separately for both the undestroyed wall and the entrance wall. But overall, all of the math is the exact same. And now we just verified that we actually have a wall prefab, instantiate the wall prefab, make its parent a wall container, which in this case is just this empty game object, just so that everything's kind of more ordered within the editor. We move its local position to 0, update its name, update its local position to the position we calculated earlier, and then rotate it based on the rotation we decided on. Then the wall data whose wall index we used to actually create this wall, indexed at I, has add wall called passing the new wall game object, which within the wall data simply assigns its local wall object to the wall we just created, and then offsets the wall with a wall position. So this is the wall script itself, which just moves its position. However, here in theory the wall position should just be 0. This was because I was experimenting with having levels where the walls would kind of pulse inwards and outwards, and I think this might just be an artifact of that time. But after calling add wall and actually inserting the wall that we instantiated into that wall data, if the wall is marked as adding an entrance, we call instantiate entrance. Now to come back here quickly, this script is only called if the wall was not destroyed. So that means its wall world index wasn't passed to destroy wall earlier. If it was, which means it was destroyed, we firstly check if we've overridden the entrance prefab. Here, this is kind of just an added option from when we called destroy walls earlier, where we can actually choose to pass an entrance prefab that we would assign to this override entrance prefab. However, here we can just assume that we haven't overridden it, so the wall prefab is now updated to the cell data's entrance prefab, which would be this i.e. the wall with the door-shaped hole in it. We update its name, and now check if the wall prefab is not null. I think this is also just relating to the end wall when we're transitioning between cells. There was also another time where I wanted one-way doors, so you walk through the door and then you look backwards and it's a wall. So this is just kind of part of that. But assuming that the wall prefab was there and everything went well, we do basically the same thing as in the wall prefab where we get the wall's x rotation. In our case here, the x rotation is 0 because it's the child of the game object that's actually rotated, but we still get it for good measure. We get the offset, which in this case would actually be 5, and we also get its y position, which here would also be 0 just because it's the children that have moved. And so then using that, we go through the exact same thing, adding its name, moving it, rotating it, essentially all the exact same steps, until here where we check if we should add an entrance. So this is once again within the maze generator. Even though we're destroying 2 walls, we're only adding 1 entrance. So if this wall does need an entrance, so we're actually trying to spawn an entrance prop, which in this case is just a simple wooden door frame, we would call instantiate entrance, passing in the new wall that we just created and added to that wall data. Then in this function, we firstly check that the entrance prop is not null, so making sure that within the cell data scriptable object it's assigned. Then if it's not null, we create a new prop called new entrance, which is just instantiating that entrance prop, and we assign the wall that we just created as its parent. Then we simply set its local position to 0. Here we don't actually have to move the prop because I believe as we're adding its parent directly when it's instantiated, and because this prop is at the position 0, 0, 0 and has no rotation, when it's instantiated, it simply matches its parent's position and rotation. So here you see the positive x entrance has its position x5 and z10 and a y rotation of 90, and the entrance frame has the position x5, z10 and a rotation of 90. This is also partially why when we created the entrances earlier, their position was set to 5 in the z instead of 4.5 like the other walls, and its children were moved back by negative 0.5 in the z. We did this so that then when the entrance frame is spawned, its position is also at 5 in the exact middle, like the parent, but unlike the actual wall plane and the railing, which are still at negative 0.5. So after instantiating it and making sure it's at the exact same position as the new entrance wall we just instantiated, we call this add prop function. This is part of the actual prop script, and I'll explain that in a second. So that's kind of the main idea. That's how the walls are actually created in the first place. And that exact same function is just called 4 times, passing in the z, x, negative z, and negative x walls. After instantiating walls, we get a chance to override the floors and the ceilings here. This is because I found about 90% of the time a flat ceiling and a flat floor is perfectly fine, so we just update the floor and ceiling materials. However, from time to time, I did actually want more complex geometry on either the floor or the ceiling, so you can add a ceiling or floor prefab within the cell scriptable object right here, and if they are added, so the ceiling prefab isn't null, we simply go through the list of current ceilings that we have, the planes, and instantiate new ones, update their positions, etc. After that, we then check if we should add props. This could be false because here within the level we can just check or uncheck to instantiate props or not. But assuming it was true, we call this create props function. What this create props function does is firstly initializes the props. So here it just checks if we haven't already initialized them. If not, we create this prop container, move it to 0, and then just add this prop script to it, which would just be a default one. After doing so, we iterate through this list of prop prefabs, which we added to earlier when, from prop spawner, we called this add prop prefab, passing in its spawn position, its actual position, relative dimensions, etc. This function at the end added this new prop to the list of prefabs. So it didn't actually instantiate a new prop, it simply added this prop info to the list, and it has a pointer to the prop prefab, but it hasn't actually been created yet. However, we did get a lot of the information that will be required to spawn it. So we iterate through this list and call instantiate prop with an element from that list. Then using that prop info, we actually instantiate the prop. So within prop info, we stored this reference to the prop prefab. We instantiate it, update its rotation based on the y rotation we found earlier. We also calculate its actual position. we're using the relative position, which was the position of the pivot we found, but to get the actual prop position within the world, because we did actually stray from just using the normal world units, which is just the base index times 10 is equal to the world position of that cell. Now, because we split up every single cell into 4 smaller prop cubes, we need to convert back into kind of node positions or cell indexes almost. And because each node index is equal to 10 world units, we can then assume that each prop index, which is 4 times smaller than the node index, is equal to 2.5 world positions. So we do the props relative position.x times 2.5, and then to explain these kind of offsets, while I know this isn't super visually intuitive, this is how we actually built the props in the first case with the prop visualizer. So here we built this 1 by 1 by 1 prop I just dragged in. This hasn't actually been moved, but this is where we built it as 0, 0, 0. And for these kind of offsets, you're going to have to bear with me for a second. So this is where we actually built the props in the first case. So here, if I drag in this chair, it's right in this corner, and this is where it was created. This is how it'll look when we actually instantiate it. But if I now actually create the level, what we see here is it was built at index 0, 0, but that's also the base index of the cell, so we need to shift it over. Here I've now disabled the kind of borders of the prop visualizer that we used to build the props, and the blue wireframes are the prop cubes that we used to create the prop in the first place. Then if I go to the level and I enable the actual prop cubes that it's using as red, you'll see that they actually do not align. They're about a quarter off each other. If I go up, it might be more visible, but here. So the prop was built in the blue, and now we need to move it relative to the red cubes. So firstly, we want to actually try and get this prop into the very bottom left of the cell that it's in, which means decreasing both its x value and its z value by 5 to move it to the bottom left corner. Okay, so here I've replaced the chair just with a cube that's exactly 1 by 1 by 1, so that's a bit easier. I'll disable the chair now, but it's the exact same prop, and it has the kind of same dimensions. So if I firstly move it -5 in both the x and z, it'll look like this. Once again, now it's in the bottom left corner, however, it still isn't aligned with the red wireframe, which is the actual prop nodes being used for this level. So I also increase it by 1.25 in the x and the z, so plus 1.25, and we end up with this. Here, I don't know if you can fully see it because the walls have been offset, but it is now perfectly in the bottom left of the prop node matrix. So we've managed to shift it from the top left within the prop visualizer, which was used to build it, into the bottom left of this cell. So if I copy its position and move it to any given cell, so maybe I randomly choose this 3 by 1 cell at 6, 5, so right here, if I were to move this prop into that cell, so simply making it the child, and then update its position to be the exact same as it was before, it is now once again in the exact bottom left corner of the cell, which means now simply by adding its relative position in the x, z, and y times 2.5, we can offset it to wherever it has to be. This is once again just using a 1 by 1 prop, but if let's say it was a 3 by 2 prop like these curtains, it starts at 0, 0, 0, which is how it was built within the prop visualizer, and then if I paste in this position we got, its pivot is now once again in the bottom left corner. So then just before here we updated its rotation that we got earlier, and here we're just creating this variable prop position as a vector 3, we're not actually moving it yet. To make sure it goes into the right position, we firstly have to make the prop a child of the cell we're adding it to. So as we saw here, this is its local position, and it only goes to this position when it's the child of this cell. So after making it the parent, we update its local position, and we add a wall offset to its local position, passing in the prop position and the prop relative dimensions. Once again, the prop position is just the bottom left of the prop regardless of its pivot. So here, for example, if I were to move this prop up to here, while its pivot, aka its relative position, is at the top, its prop pos would still be considered this square, the bottom left of it. So we pass that in and the relative dimensions, and then it basically compares the prop's position to the cell walls, which it gets by doing the dimensions of the cell times 4 minus 1 to get the positive x wall here, and here the positive z wall, or 0 in this case would be the negative x walls, and 0 here would be the negative z walls. This works because when we passed the prop position earlier, we found its sort of relative index by subtracting the cell's base index times 4. This just means that we can find out whether or not it is adjacent to a wall and which wall. So here, if it's adjacent to the positive x wall, as in for this cell, it's trying to spawn like here, and earlier we defined this local offset variable, we subtract the cell data's wall offset from the offset's x component, where the wall offset within the cell data was defined right here, so 0.5. And what this means is after checking which walls it's actually adjacent to, so it could be more than one like in this case, we return the offset that we found, and then we add this offset to the prop's local position. What this means in practice is just because we actually spawned the prop and we got its position using these sort of prop nodes, if it's against a wall because it was made in the top left corner, like in this case, the prop in theory should have spawned over here. However, because the walls aren't at 5 and 5, we've offset them. When it is spawned, it's automatically moved forwards to adjust for that. This can be seen here where the props actually go out of their bounds a little bit because they've been moved to the left so that they don't actually intersect with the wall. And after adding that wall offset, we add the prop to this cell props object that we created earlier. What this actually looks like is when we create a prop, we just have this empty game object with only the prop script and then references to its children. The children can have renderers, box colliders, even only a box collider, rigid bodies, etc. But when this prop is instantiated, so created for the first time, with this list of children, it calls this verify children function, which goes through every single child game object and checks if it has this renderer or collider or rigid body. And if it does, it adds it to a list of these specific things. So when we're calling here add prop on the cell props object, we're passing in this prop. We check if it's interactable because interactable props can actually move from one cell to the next. But if it's not, we simply add it to this list of child props, which just means now if we were to toggle the prop renderers, so make them invisible, we firstly go through all of our children that had renderers, and then we go through the list of child props, calling the exact same function on the child props. So this is kind of recursively going through. This just means that with one function right here, toggle props, by calling it on cell props, we're also calling it on every single child prop that we add. So in the game, what it would look like for this cell is we created this props object, and then that just has a reference to the door frame right here, and the door frame has a reference to the individual components of the door frame. Same for here, we have maybe a bed, so it has children with the bed itself, the metal bars, the feathers, and then colliders. So if we were to try and disable this cell, we would just call disable props here, and then each of these that are a prop would call disable props on its own children. So that's briefly how we create the props. Then we do some other stuff and update the cell's materials, which is just setting the floors and the ceilings to whatever we want them to be. However, as you might have noticed, these props have another type of child, which is spawn points. So when we first instantiate the prop, we also verify these spawn points, which is just going through and making sure they're not null. But spawn points, unlike props, are places where there's supposed to be something when the player is nearby. Whereas the props are created at the beginning and they're moved and then they're kind of not touched for the rest. The spawn points are more dynamic. So here, if we look at this per cell prop, this flat ceiling lamp, it not only has a child, which is a plane, i.e. the thing that we can see on screen, but it also has a spawn point. So when the player collides with the spawn point, i.e. the spawn point is close enough to the player that we would actually want to bring an object over, what it gets is an object from this object pool. Now, to explain briefly my object pool, it's a singleton, but I have a list of object types where each type has a boolean whether or not we should use the pool, and then an object pool type and a list of object variants. So the object pool type defined here is like lights, doors, audio sources, etc. Whereas the list of variants, these are just variants of the exact same type. So here you can see for element 0 in my object pool in the editor, I select use pool and then I select light as the pool type. And then here I have a prefab for what that light should be and the number to spawn. So the prefab is literally just a regular point light. So this means when I start the game, it'll just spawn 20 of these lights, disable them, and then put them at 0, 0, 0 in the world. And here, this is an example with multiple variations where I have the one type door, but then I have different variants. So door prefab here is just a template prefab, whereas the hospital door is what we saw before within the hospital, and the bedroom door is just this other door which we haven't really used. But as you can see, when we actually start the level, we're only spawning 10 doors. There's only 10 doors around the entire map, which means instead of there being a door in every single door frame, it's just when the player is close enough and can see that door frame, we teleport a door over to it by using the spawn point. So when this object pool is actually created, we firstly initialize these pools and populate them, spawning what we actually need to. I won't exactly explain how all of this goes, but what we actually create at runtime, the pool that we're getting things from, is a list of lists of an array of game objects, where when trying to index through the list, the first index here, I, is for the different types of pools, so doors, enemies, lights. Then the second index, this J, is for the object variants. So in the case here where we have multiple variants, this would be the J value. And then here the third value, the K value, is for the individual object, the individual prefab that was instantiated. So here on the object pool in the game, the value that was stored in I is just here 0 for lights, 1 for doors, 2 for enemies, and 3 for audio sources. Then here within the doors, these would be the different variants. So the J value would indicate if it's a door prefab, a hospital door, or a bedroom door prefab. Then finally, the K value would actually be the index within this list of 5 door prefabs, or within this list. So here for the lights, this would be 0, 1, 2, etc. So after we create these pools, you'll see if I select all 20 of the lights here, they're all at the exact same position and they're all disabled at 0, 0, 0 in the world. So to actually get an object from this pool, we firstly have the script of spawn point, which is just a more general use case, where we have a collider that's triggered by the player. So here if I go to the ceiling lamp prop that we saw before, it was a per unit prop. It also has this spawn point here. And the spawn point has a box collider. If you can see this tiny green square, this is its box collider. This is the spawn point of sorts. Then now if I go over to the player, here you have a massive green box. This massive green box is the player cam's load area trigger, which means that when this collider overlaps with this tiny collider on this spawn point, this function is automatically called on trigger enter. This function is called automatically in Unity when the collider attached to the game object, which has this script, enters a trigger. So this being the collider attached to this script, the spawn point, and this being the trigger that's around the player. What this means is that whenever the player is walking around, all the things within the object pool are only actually moved in the world and used when they're within this area, this volume. So that is how we're actually initially getting the object from the pool. So this spawn point has not only this collider, but it also has this object. What this object actually references is going to be the object from the object pool that we get when this collider is triggered. So for the light, it would be pointing at one of these objects, one of these pooled lights. We also have some audio source things here in an audio object. I'll ignore this for now, but we'll come back to it shortly. Then finally on the spawn point, we have this object type, which is later used to actually find which type of object we want to get from the object pool. So once this trigger is collided with, we firstly check that the object that we're referencing is null or it's inactive in the hierarchy. What this is verifying is that we don't already have an object. Maybe we grabbed an object from the pool and haven't released it. So if one of these are true, we still set the object to null, and then we call getObjectFromPool. When we call this, we now assign the object which was null to whatever is returned from this function, which is referencing the object pool, and calling getObjectFromPool, passing in the object's type, which we saw was defined here in the spawn point, and a variant number. Now this variant number is only actually relevant if there's more than one variant type. So here, if this list of variants is greater than 1. So in the case of the lights, because there's only one variant, we can always just pass in 0 because there's only one element within the list, which would be indexed as 0. We then make sure that the object that we got is not null. So here within the object pool, when we call this getObjectFromPool, we firstly check that the type is not nothing. Then we make sure the request is valid, ensuring that the type and the pool type and the variant are all actually in the object pool. Then we iterate through the array of the objects that were actually instantiated, so that variant prefabs, make sure they're not null, and make sure they're disabled within the scene, which is just here when they're grayed out, they're disabled. And if we find one, we return it. If we don't, we return null. This could be because the object pool is empty, so that means every single light here, for example, is already being used by another spawn point. But assuming everything goes well, we now have an object. So we firstly move it, where we set the object's position to the exact center of the collider. So here we have the spawn point at this position, but then we also have a collider here that's offset. So when we get the object from pool, we're actually moving it to the exact center of this green cube. After moving it, we update its data, which for the generic spawn point doesn't do anything. However, because this is just a template class, we have this light spawn point, which derives from a spawn point, and that includes this light data scriptable object. What this includes briefly is just a description of what we want the light to look like. So within the game here on this light spawn point, you have this light data scriptable object that just includes the radius of the light, what kind of light it is, its color, its intensity, its shadows, etc. And we assign this to the spawn point prefab before instantiating the level. But what this means is after we've gotten this generic light object from the pool, we can actually update its data. Here I have a light object script which is attached to every single one of these point light prefabs that are pooled, so right here. And in this script, when we call update light data, passing in the light data that we stored on the spawn point, it just goes through and updates all of its own data. What this means is I can just use this generic point light, and then based on the spawn point, like for example, if I wanted a candle, I could still use the exact same point light prefab, but just update it so that it's fit for the situation. And after updating this light object's data, we simply enable the object. So firstly, the player's trigger called this event because we were close enough to the object. We then made sure we didn't already have an object from the pool. We then got an object from a pool, moved it to the center of the collider, updated its data, and set it as active. So now we have a light within the scene. Now quickly coming back to this audio source data and the audio object, I just created this because I found in a lot of cases when we're spawning something like let's say a light or a door, as is the case here with this door spawn point, the entrance frame has the door spawn point here, and this is just its collider, so this is actually where we're spawning the door's pivot. A lot of the time when I'm actually grabbing something from the pool, I would also need an audio source. So for the light, the background buzzing when the player walks by, for the door, the sound of it opening or closing. So instead of having to create a different spawn point for an audio source every single time I created a light spawn point or a door, I allow the user to instantly select to add an audio source, which is also automatically grabbed from the pool when the main object is grabbed from the pool. To be able to grab an audio source from the pool, I include audio source data, which just looks like this. So whether or not it should loop, how loud it should be, how it should sound spatially, so how close you have to be for it to actually be audible, and then a passive audio source clip. So for the lamps, this is just the lamp buzzing that you hear. This is just always playing and it's looped. However, as is the case for the door, I also allow you to add one-shot clips. So these are clips that are only played a single time, and here you can override its volume, but it's just a list of clips. These are just all different sounds that the door can make when you interact with it. So there's two different types of audio. The passive one that's just played 24/7, and then these one-shot clips that are only played at a specific time based on a certain set of conditions that are being met. So here if we look at the door spawn point, which is once again deriving from this spawn point, we have this door object, and then a new enumerator, these door types, which are just default hospital, bedroom, dark bedroom. And for the door, a few other things are happening because while we're not necessarily updating data about the door like we were when we were grabbing the point light, we do also need to track the door's position, so whether it's open or closed, and if they are open or closed, which direction they are open or closed in. Because if we look here, the door's spawn point is on the left of this wall, so if I, the player, were standing here, the door would open outwards. I coded it so that the door is always open away from the player. However, like the lights, once the player moves on, the object that we grabbed from the pool is then returned to the pool. This means for the generic spawn point class, we have this onTrigger exit, which as opposed to the other onTrigger enter, which is called when the collider enters a trigger, this one is called when it exits one. So we firstly check if we should return the object. For the generic class, this is always true, and then we return the object of the pool. So if there was an audio source that was grabbed from the pool when this object was grabbed in the first place, we return that. Then if the object isn't null, we disable its components, disable the object, and set our local reference of the object to null. By disabling this object, that means that the object is no longer active in the hierarchy and it can be grabbed by a different spawn point and reused. However, for the doors, because we need to maintain this status, so when it's grabbed again, something might have changed, it might no longer be open, we do also store that. So here, if I come over and I select this spawn point, you'll see it's enabled, but there's no light here. This is what it actually looks like in game, so it's just basically a dark room. Then, if I come over and I select this player's trigger, so the area which is considered within the player's sight, you'll see that as I, the player, turn to the left and this green box eventually overlaps with the spawn point's collider, there's suddenly a light there. Now as I exit it, it's gone. One more time. There are lights. There are no longer lights. And here, if we look at the object pool, there's already a couple lights that are in. So these two ceiling lights, the per cell props, and this other side lamp. Here you'll see the only real difference between them is the range, but now if the player turns and comes back, if you look here within the object pool, you'll start to see what I mean. Here there are no lights, every single light is disabled. However, now as I turn, suddenly all of the lights have been enabled and all of these lights have been updated so that they're actually being used. However, if we were to just track this one light, so the light here that's being used for this side lamp, as I turn away it's disabled again, but now when I come back, you'll see the exact same light is being used over here for the ceiling lamp. So its data was updated and it was moved again. And a different light is being used for this side lamp. For the doors as well, here as I grab a door, when I look away, there's no door there, nothing. Then as I look back, the door gets re-added. As well, if I come over and I open it, it's now opened facing away. But here as it gets disabled again, there's no longer a door. And yet, when I turn back, it's still within the same position. And I can even, by moving away to the other side, now as I've come back over, you'll see the same door that I selected that was initially there is now being used all the way over here on the opposite side of the world. And the door that's now here in its place is this door over here, but its position has been maintained. Here you can also see an example of the audio sources being grabbed and released automatically. So this light right now has a child, which is an audio source that has its hospital lamp buzz. And then as the player turns away, the light no longer has a child and the audio source has been returned. So that's kind of the brief of the spawn points in the object pool. This, I believe, is a pretty common class and a common use case, so I won't go into it much further. However, it does lead me into my next topic, which is I've created this object pool to save on costs like lighting and rendering for objects, which I think will be cost intensive. However, there's also here a chance that if I were to only use this trigger and collider system, a light could be enabled and grabbed from the pool just because the player's in close proximity to it, but it could also just be on the other side of a solid wall. This is in part because the player's load area trigger is large and it covers most of its camera's view distance. So here as I turn the player, even though this entire cell is invisible to the player because it's surrounded by walls and the player is on the other side of a wall and there's no way for it to actually see it, it might still grab a light from the object pool. So to solve this, I implemented something called a load area trigger. So before going straight into the load player area and how it gets created and what it does, unlike before where for a 2x2 cell you only had one cell, and then when you looked at the indexes of part of it, it just pointed back to the same cell, this cell node matrix is much more similar to this visualization, where while this is a 2x2 cell, there are actually 4 individual cell nodes within the matrix. Each of these nodes has a pointer to the cell which occupies that space. So this node within the node matrix would point to this cell within the cell matrix. The same for all the other nodes. It also has a load status, which here for our demonstration will just be unloaded or loaded. We can ignore this. And it has the base index of the cell. So here this isn't actually a separate variable, we're just returning the cell's base index. We then also have the node index. So here for this node, its node index would be 0, 1, but its base index would still be considered 0, 0. And then it has this array of next nodes. Here, as you see, the node at index 0 within the next nodes is the positive Z node. Then the node at index 1 is positive X, index 2 is negative Z, index 3 is negative X. I did it like this because then if we wanted to find the positive Z node within this next node's array, we could simply plug in the direction positive Z within this direction's enumerator, which itself is equal to 0. And then let's say for negative X, within the enumerator it's equal to 3 and it's at index 3 within the next node's list. We also defined this null node up here. It's read only and it has the values -1, -1. This is because none of the next nodes will ever have this value. But so now when we create a new cell node, we pass in the cell and the node index, where the cell is the actual cell within the cell matrix and the node index is just the node index. So we assign this cell value to the cell we passed, initialize this next node's array with 4 indexes because we have 4 directions. Then we call this function setNextNodes. Now firstly, when you think of these next nodes, what I want you to think of is just like the wall world indexes, where the next node is basically pointing to the node on the other side of the wall. However, unlike the wall world indexes, these are only actually present if the cell node in that direction is accessible. So within the same cell, let's say this, we would only have these next nodes if the adjacent node that is pointing to is accessible. So here, we'd have 2x3 and 1x3 on the other side because they can be accessed even though they're within the same cell. So to get these, we firstly initialize each of the indexes as the node index and then plus 0, 1 for the positive Z, which let's say for this node index, when we initialize the positive Z, we just do this plus 0, 1, which turns out just to be 1, 2, which is the positive Z node. So it's very similar to what we were doing before. However, we then need to find out if that node is actually accessible. So we initialize all of them to the correct next node, but here we're checking if the node is at the top of the cell. So if it's 1x1 or 0x1 here, or any of these other underlined values, which are just at the most positive Z part of the cell, which we get by comparing the node's Z index, which here would just be 1, and we see if it's equal to the cell's base index plus the cell's dimensions minus 1. So here the base index's z component is 0, plus the z dimensions, which here are 2, and then minus 1, which is equal to 1, implying that this is at the top of the cell. We do a similar thing here to see if it's all the way to the right of the cell with the node's x index, using the base index as x component, the cell's x dimensions, and the node's x component. And then to see if it's at the bottom of the cell, it's just if the base index is equal to the node index. So this update next nodes function is only actually called if the node is at the top of the cell. Because we know if it's not at the top of the cell here or here, no matter what, there will be a path leading directly upwards from it. We call this update next nodes function, passing in the index of it within the next nodes array, so for positive z0, and a list of positive z paths leading out of the node. So we call get positive z paths on the cell, and then we get the paths from the wall using the positive z walls, where we iterate through every single one of the positive z wall datas, and only add it to the list if the wall's been destroyed. By it, I mean the wall's world index. So, regardless of if we were looking at this node or this node, if there was a path here so the wall was destroyed, we'll still return 1, 2, the wall world index. So we return that list as one of the parameters for this update next nodes function, and then we go through every single one of these neighbors, so the nodes adjacent to a wall that's been destroyed, and compare them to the next node at that index, so for positive z. So if this wall was destroyed, and we were looking at 0x1, we would have instantly computed all of the next nodes, and its positive z would have been 0x2 because we did the node index plus 0, 1, and then we found that that node was at the top of a cell, so we got the positive z paths of that cell, which would have just returned 1, 2, and after that, when we iterate through the list of neighbors, which here would only include 1, 2, we would compare the neighbor to the positive z next node, which is 0, 2. And only if this positive z next node is equal to one of the neighbors do we allow this positive z path to remain. If it's not equal to any of the positive z neighbors, then we set its value to this -1, -1, which is the null node from before. What this means is if this wall was destroyed, this node would not have a positive z path. However, this node would, and it would be 1x2. But this node would still have a positive x path, because they're within the same cell, so it would store 1x1 here, and this node respectively would store 0x1 here. So here, when we actually check if the node has a positive z path, what we're actually checking is that the positive z node at index 0 does not equal this null node. So after we've generated the maze and destroyed the walls, what this actually ends up looking like is something along the lines of this, where here if there's a gap, then that means there's an entrance or an exit leading out of the node, and within each node, these thinner lines indicate that it's just part of a bigger cell. So here, this is actually a mistake, this should be 0x1. But if I was at this node and I asked, where can I actually go from here? Out of all of its next nodes, there's only one possibility. And each node is still storing the base index of the cell, as well as the nodes that are directly accessible from it. So those are kind of the cell nodes. But to briefly explain how the load player area gets created, when we actually click play, this level manager firstly gets all the levels we want to spawn, and then spawns them, iterating through the list of levels and calling spawn level, where we update its data, initialize it, generate the level, and generate its maze. Then after spawning it, it checks if we're using this load player area, and if so, we disable the level, calling this function, which waits for the level to have finished generating, which means its status is equal to complete, and then calls this disable level on that level, which just goes through every single cell and calls disable cell, which makes the cell disable its walls, floors, ceilings, props, spawn points, and set this bool as false, meaning the cell has been disabled. So once we finish iterating through this list of levels and disabling them if need be, we then spawn the player as well, which waits for the very first level to have been completed, meaning it's fully generated because that's where the player will spawn and we don't want them just falling through the floor straight away. Then we instantiate the player, move it to the correct position, and assign it to a level. And after spawning the player, we call this initialize load player area function. What this does is it waits for the last level in the list that we're actually spawning to be complete and for the player to have been spawned. We call this initialize load player area, passing in the very first level cell matrix, the player controller, so the actual player object, and a boolean which basically says whether or not we actually want the cells to be enabled and disabled. So we call this on the load player area, which is a script on the exact same game object as the level manager, where we can just select which levels to spawn, and we have this boolean to use the load player area. So when we call it, the load player area firstly creates a node matrix which is the exact same size as the cell matrix that the first level had, copies the reference to the player, and gets the player's transform component, which basically only stores its position, rotation, and scale. We then iterate through the entire node matrix and create a new cell node at every single index, passing in the cell at that index within the cell matrix, which would be the exact same for this node, and this node, and this node. They're all the same cell. And we also pass in the X and Z index of this node within the node matrix. While all this is happening, the load player area actually has a fixed update running. Without any other script doing anything, maybe 60 times a second, let's say, this function is running. So firstly, in this function, we're making sure that the player's transform is not null and the node matrix is not null, which means we'll only actually be running the code within this statement after the load player area has been initialized, so the player transform has been set and the node matrix has been created. Then once it's been initialized, we call this function getNewBasePosition. So this load player area has two kind of main positions, a current base position and a new base position. What these actually store is they convert the player's position within the world into an index within the node matrix. This is because while the center of each node is at the position within the world equal to 10 times this index, the player might be anywhere within the node and we would still have to convert that into the node's index. To quickly demonstrate what I mean, this node is at 0, 0. It's a 1x1 node, and its position is also at 0, 0. Now I know that the player is in this cell right now because the player's position is 0, 0, but this is also constantly changing. So if I were to move the player now down into this bottom left corner, its position is now negative 3.4 in the X and negative 2.8 in the Z, but I still need to get this 0, 0 based on this position. Similarly for this 2x2 cell, we're still trying to get the node index. So because of its cell base index, we know that the node in the bottom left is at 2, 1, and therefore the node in the top left is 2, 2, the node in the top right is 3, 2, and the node in the bottom left is 3, 1. However, once again, the player could be anywhere from the top right, 23 and 23 in the X and Z, to the bottom left, so 16 and 15 in the X and Z. But using this 16 and 15, we need to get 2, 2, which is this node index, because its base index was 2, 1 and it's 1 above in the Z direction. So to do just that, we call getNewBasePosition, which converts the player's position into a node index by doing the player's position plus 5 divided by 10. So the node here, 2, 2, which has the world position 20, 20, its bottom left, which in our case here for this 2, 2 node would be right here, is at 15, 15 in world position units, and its top right, which is here, being the maximum, is at 25, 25. So here with the player in the bottom left, it's at 15, 15, and at the top right is at 24, 24, but basically 25, 25. So we need to convert any value between those two values into 2, 2. So we take the player's position in both axes and add 5. I'll do it for both the minimum and the maximum. However, the maximum here would really be 24.9 because the maximum is still exclusive and the minimum is inclusive. But for both the maximum and the minimum, if we add 5, for the minimum we get 20, 20, and for the maximum we get 29.9, 29.9. Then we cast both of these values to integers, which removes any decimal positions. So these become 29, 29. And then when we divide by 10, because it's integer division and there's no decimals, we end up here with 2, 2, and here also with 2, 2. Because 29 divided by 10 is 2.9, yet because they're integers, we once again remove the decimal. So from 15, 15 in the bottom left corner, all the way to 24.9, 24.9 in the top right corner, by doing this, we end up getting 2, 2, which is the node's index. There's also subtracting here a level offset because here briefly, when we spawn two levels, this level is offset, so it's actually placed at 100, 80, so the offset would actually be 10, 8, which means if we bring the player up to this 0, 0, the very bottom left cell of this entire level, if we found its position, it would be equal to 10, 8, which is this other level's offset, so it would convert that position to 0, 0, and then offset everything else as well. So that's how we get the new base position. Then, because this is running every frame, we actually only want to do more things if the new base position isn't equal to the current base position. So that would mean after we calculate this, we keep recalculating it, getting the same value until the player maybe goes up and now he's barely in 2, 3 right here, at which point we would be comparing 2, 3 to 2, 2, see that they're not equal, and then run this. Firstly, updating the new base position to the current base position, so we're not constantly running it multiple times while we're still walking around 2, 3. Then we check if the player's X position is greater than the node matrix X dimensions, This is just because, as we saw here, the player can actually walk through this wall, and that would trigger this level to be disabled. So that's actually all we're checking for. It's just if the player's left this level, which would mean when we find the player's position, it would actually be greater than 9, which is the x dimensions of this level. So that's an edge case. Then here we check if we're actually toggling the cells. So this just means we could still run the load player area, as is the case here, but we're just not actually updating anything. We're not unloading or loading anything, which is why the spawn points don't actually work, because they get unloaded by default. But assuming we are using the load player area, now we call this function visit nodes. So starting from now, what we're really trying to do is get a list of nodes that we want to load and a list of nodes that we want to unload. So here, once again, we have this node matrix. If, let's say, the player was standing here, the nodes to load would obviously include the node that the player is currently standing in, this node because there's a clear line of sight, maybe this node because it goes up. So if the player was in the bottom left corner, we would still be getting the exact same node index. We don't actually know where the player is exactly within the node, but there's a chance that it could see these nodes over here, so we would load them just in case. The nodes to unload would include here 2, 1, because the player is in this cell. For it to be able to see whatever is in this cell, the player would basically have to be able to see around a corner. So this would be considered a node to unload. On the other side as well, these would all be nodes to load, and maybe also this one. But once we go back to the right after going to the left, that is now a node to unload. There are also bounds set because the player can only see so far. So after a certain point, even if the player was here and we were looking in a straight line, maybe this would be unloaded as well just because it's too far for the player to see. But we don't need to worry about that right now. So here we have this list of nodes to load and nodes to unload. We firstly clear both of them. Another thing worth mentioning here is while these are lists of nodes to unload and nodes to load, they will ultimately become cell-based indexes because we can't actually unload individual nodes within a cell. So it's more like if, let's say, the player was standing here, he would be able to see what's in this node because he might have a line of sight here, but he would definitely not be able to see what's in this node because he'd have to see around the corner. However, because they're all part of one cell, we still just have to load that entire cell. Because as we'll see later on, when we're calling load cell, we are calling it on the cell node firstly, but then that node is using its reference of the cell to load its components. So that's why we initially add the base index of the node the player is currently in. Then moving on, this function is more of an edge case once again. It's just because I wanted one-way doors previously, which are similar to this end wall within the cell where once you go in it, you can't go backwards. However, I wanted to have them within the level themselves, which would in fact mean that, similar to the case right here, you would think from this node that you would be able to go up here, but from this node's perspective, there is an actual wall here. So that's just kind of what this is. We can ignore it. But now we actually start trying to get the nodes that we want to load based on the player's position. So these are nodes that are visible to the player. Here I actually have an early drawing of what I actually wanted this to accomplish, wherein if it went to the left and then to the right, it would be considered unloaded, or if it went up and then down, it would be considered unloaded. I also just found this one, which is just for pushing the path. I don't know, maybe I'll include this, but anyway. We firstly start checking the positive Z paths. So to do so, we check if the cell that the player is currently standing in. So using the player's new base position X and Z within the node matrix, we can access the cell, which is stored right here within this cell node, and then check if that cell has positive Z paths, which within the cell script just returns true if when we get the positive Z paths, there's more than 0. Here, initially, if we're still just using the cell components, this is because even if the node has a positive Z path, the cell might not, which means if let's say we were just looking at this node, it would say, oh yes, we have a positive Z node, so we would need to go and check for the direction and do all this other computation. However, we know that this cell doesn't actually have a positive Z path because it's at the end. And we know that no matter what, when we actually load this node, it'll load the entire cell. We firstly check if the cell itself has positive Z paths just so that we don't end up actually just trying to visit things that don't lead anywhere. So if it does have positive Z paths, we then iterate over every single one of these positive Z paths. So still looking at the cell within the cell node and getting its positive Z paths. Just here within the cell getting positive Z paths involves returning the list of wall world indexes for walls that were destroyed. So now we iterate through the list of positive Z paths. So even if we were looking at this node in particular, we would be iterating through the list of positive Z paths for this entire cell. So here that list would only include 0, 2, but if this wall was also broken, it would also include 1, 2. So the list would be 0, 2, and 1, 2, regardless of which node we started in. And we're only using the wall world indexes, or now the neighbor node indexes, if the wall has been destroyed. So we iterate over them and then call this visit positive z function, passing in both the current cell, which in this case actually corresponds to the wall world indexes that we got from the positive z paths. So when we're calling this function, we're passing 0, 2 as the start node, and we're also passing the return value from this get direction from base function. This is basically returning a secondary direction, because when we call visit positive z, you'll see the direction default values are set to positive z already. But there is a chance that to get to this wall world index, we actually had to make another step. So here in our case, if we started at 1x1 and we passed 0x2 as the wall world index, or the next node, to call this visit posit function, it would initially just pass positive z as the directions. However, we actually also had to go negative x and then positive z, and that's what this function is essentially returning. So we pass in the direction that we're supposedly going in straight away, so positive z here, and the next node that we're going to start the call pos z paths from. So from 1x1 we would pass in 0x2 and positive z, and within this get direction from base function, we compare the path position, i.e. 0x2, to the current base position, which is 1x1. So because we're going positive z, we only actually check the x component of the path position and the base position. If the x component doesn't change, then this is the case, we're just going positive z. This would be true if the player was standing in this node and we were looking at 0x2, or if the player was standing in this node. However, if the path's position.x is smaller than the current base position.x, which is true in our case where the player is standing at 1 in the x, and the path is at 0 in the x, we can assume that a step in the negative x was taken before going in the positive z, which is true, we had to go negative x and then positive z. On the other hand, if the path position's x is greater than the current base position's x, then we must have taken a step in the positive x first, which would be the case in this cell if the player was standing here and we looked at 3x1 as the positive z node, because the x value of the base position is smaller than the x value of the path position. So that would imply we're not only going in a positive z step, but also a positive x. The process of checking if the cell has a path in that direction, and then iterating through the paths within that direction, and checking whether or not there's an offset between the player's position and the position of the path, happens for every single direction, so positive x, negative z, and negative x. But once we verify whether or not there is an actual initial offset, so for a 1x1 cell there never would be, because no matter what, everything is directly accessible, we call this visit positive z function, passing in the path position and the direction that we got, as well as a default value of positive z, because we don't actually pass a third variable to this function, so the default value of positive z is used, but the start direction is updated in our case to positive x, because we noticed that we took this step before going positive z. So in our case, starting from here and going here, the value we passed in for current is 0, 2. The start direction we passed is negative x, because we found that we took this step to the left, and the previous turn would just be positive z. So because this function will later be calling visit positive z if there's a positive z path recursively, as well as visit positive x or visit negative x, we implement some break conditions here. Firstly, checking if the node that we're currently at, so the one passed, if that node's base index, so the cell's base index, is equal to the base index of the player, we return, or if the nodes to load already contains the current node that we're in. So here this is trying to prevent things like, let's say if this wall was also broken, there's a chance that we would go negative x, positive z, positive x, and then negative z again, and then we would just keep doing this loop and the computer would break and everything would go to hell. So we check if we've already looked at the node or if it's the node that the player's in. If not, we can continue. We then check, because this has been called recursively, if the start direction or the previous turn direction are equal to negative z, which would mean that, for example, we started in this node and then checked the negative z, which was 2x1, and then we kept going to the right, let's say, and then we tried to go up. So this would be calling visit positive z, but the function would have the start direction of negative z and then the next turn of positive x, because we went down and then to the right. When we call visit positive z here, just because it's adjacent to this node, we would notice that one of the directions, the start direction here, was negative z, which means that we've gone down and then up, implying that there's a corner somewhere along the line, so this node would never be visible. In which case, we actually check if the node directly below the current node is the same node. So what that would mean here is we would firstly actually go from this node to this node. And because, as we saw before, we actually would still want this node to be loaded, but we can only actually load the entire cell, we check if the node that we're currently at is the same as the one below it, only here for the positive z, and if they both have the same base index, then we simply skip and return. But if they have different base indexes, which would mean we went from here to here, as opposed to the same base index where we went from here to here, then we would call this unload positive z function. I'll go over this shortly, but I'll firstly run through the rest of the logic within this positive z. Another reason briefly for actually trying to unload the positive z, even if neither of the directions were negative z, is if the node isn't in bounds. So what this means is we're basically comparing the difference between the node that we're currently at and the current base position of the player. And we're comparing that to this load area radius, which within the editor is simply set here as 4. But if the player is standing here, let's say it was only 2, so the player cannot see anything after this line, we would basically check the distance between these two, and because it's greater than 2, instead of simply quitting and just no longer checking if there are more nodes in that direction, we have to try and unload the nodes in that direction, because if the player was here and this was loaded, and the player was here and it was still loaded, and then it's here and it's no longer accessible, there's a chance that maybe this node or this node are still loaded. So we have to call this unload positive z to basically do the opposite of visit positive z, wherein it recursively tries to get a list of the nodes that were previously loaded so that they can now be unloaded. I'll explain the unload functions shortly, but here just assuming that everything went fine, so it wasn't too far away from the player, and at no point has the direction been negative z, we would firstly check if the node that we're currently at, so in this case 0x2, if that node has a positive z again, which in this case it does, it has 0x3. So because it has this positive z node, we call the exact same function visit positive z, but instead of the current node that we're at, we pass in the current node's positive z node. So here, this current node's positive z node is 0x3, and we pass the same start and previous turn directions, which would just go back up here, and this node would then check if it has a positive z node, if it's not far away from the player, etc. So that's sort of how this works recursively. So if the player was here, it would firstly get the node 3x1 as the first positive z node, and call visit positive z, passing positive z and positive z as the direction. This node would notice, oh, I'm still close to the player and I have a positive z node. I'll also call the exact same function. Then from this node, it would say, oh, I'm still close enough to the player. I also have a positive z node. I'll go up, etc., etc. Until there's a wall, or it's too far away from the player. After checking if it still has this positive z node, it then makes sure that neither its start direction or its previous turn direction are negative x, and that the node that we're currently in has a positive x. So here we passed in visit positive z and we arrived at this node. It also noticed it had a positive z node, so we went up, but then it'll also check if it has a positive x node, which it does in this case. So it would try and call this visit positive x function, which is just passing in 1x2 as the current value to a visit positive x function instead of this visit positive z, which is essentially the exact same, checking the positive x walls and making sure the direction was never negative x. However, here in our case, because while we called visit positive z, we did still have to take the step to the left, which we got as the return value from get direction from base. So we know that we actually have visited negative x. So there's a corner, and therefore this visit positive x is not called. But let's say if the player actually started in this node, so therefore get direction from base only returned positive z, this node would say, oh, I have a positive x node, and neither my previous nor start direction are negative x, so it will continue and call visit positive x with this next node index that just corresponds to 1x2, and then that node would firstly check if it has a positive x, just as here the positive z node firstly checked if it had a positive z, but then it would also check, oh, I also have a positive z. It would check its start direction, which was positive z, and its previous direction, which was positive x. Neither of them are negative z, so it would be able to call the exact same function and go to positive z, which would bring us back here with this node. But once again, this only works if we start here. Because we started here and our start direction was negative x, this can no longer be visited. So because it can't be visited, because the start direction was negative x, we would still check if the node has a positive x wall. So because now we're trying to unload nodes, we would still check if this is available, because the first function might actually fail here because there's no positive x node. So this would fail and it would move on here. So that's why we check that it still does have that node, or else we might be trying to jump over this wall and unload from there. But because we've established it has a positive x node, we call this unload positive x function, passing in the node that we're currently at, so here 0x2, as well as the positive x node, so in our case 1x2, which corresponds to the positive x node here. And because this function also has default values of positive x for a start direction and a previous turn, we pass in positive z as the start direction because this visit positive x node was called after going positive z. So we call this unload positive x with the start node, current node, start direction in previous turn, which the start node turns out to be 0, 2. The next node is 1, 2. The start direction was positive z, which we passed because this unload positive x function was called from visit positive z. So here it was passed as positive z. And then finally positive x is the previous turn because that's the default value here and it wasn't assigned. So similar to the loading positive x, we make sure that the node we're about to visit, its base index isn't equal to the base index of the node that the player is currently standing in. And then because we know we're supposed to unload in the positive x, we just check if the node that we're at now has a positive x, and if so, we just unload from that node, passing in the start node and the current node's positive x node, as well as the exact same two directions. So in our case, when we're calling it from this, the only thing we're actually changing is this next node, which is going from 1, 2, which is this node index, to 2, 2, which is that node's positive x node. We then check if the node that we're currently at has a positive z node. So here at 1x2 we do have a positive z node, 1, 3. And if so, we also check if the positive z node is loaded. This function is basically just returning whether or not that node is loaded, which it gets from the cell. And then we check that neither the start direction or the previous turn direction is equal to negative z, which is the opposite of the node we're trying to unload, which is positive z. Here, when we actually perform that check, this function will return true if the first direction is equal to the second or the third direction. So this alone will return true if this is equal to this or if it's equal to this. And then we take the opposite of that. Now, because we came here initially from positive z and we passed in positive x automatically, this will return false. So because we're taking the opposite, we will actually execute this, which is just calling basically the exact same function as before, passing in our start node, but instead of like here where we're passing in the positive x node of the current node, we pass in the positive z node. And here then we pass in a copy of the start direction in the previous turn. So going to unload positive z, we basically do the exact same thing. Here, after calling unload positive z using this as the current, we still have positive z and positive x as the previous directions. We check if there's another positive z node. So here there's not, so we don't care. And then we check if there's positive x or negative x. Here the negative x, we know that there's none, but we see that the positive x actually does have a node right here. And neither the start direction or the previous turn is equal to negative x. They're equal to positive z and positive x. And we know that the node has a positive x, so we call unload positive x once again. Calling it on this node, go through the same thing, noticing it doesn't have a positive x node, so we ignore that. Then for the positive z node, it also doesn't have a positive z node, so we ignore that. But it does have this negative z node. However, while it does have a negative z node, and the node might or might not be loaded, when we compare the start direction in the previous turn to positive z, which are positive z and positive x, this function will return true because the previous turn is equal to positive z. And as we're taking the opposite, this if statement fails. So we won't actually go on to unload negative z. This is because if we were to do so, then we would end up coming down here. However, what I didn't mention earlier is with the positive x, when we are unloading positive x for the first time, this unload positive x, which is using the 2x2, so going to the right, would have called unload positive x from 2x2 straight away before going to the positive z. So if we actually allowed it to go positive z and then negative z, we would end up calling unload negative x on this first from this node, and then unload negative z from this node going down here. So just repeating the exact same thing twice. That's why we're storing the start direction and the previous turn direction, so that we don't end up just going back on ourselves. So assuming that now from this node there's nowhere to go, all this function actually ends up doing is adding the current node, which here is 2x3, to this list of nodes to unload. And that's basically the same endgame from visit positive z that we started at, because it checks the positive z if it can keep going, checks if it has a positive x node and it can load it, if not, if it has a positive x node and it can unload it. Same for the negative x, checking if it has a negative x node and can load it, or if it has a negative x and it should unload it. And after all of that happens, we just add the current node to the list of nodes to load. So after going here, all of that, this node, the 0x2, just gets added to the list of nodes to load. You'll also notice within the positive z, the one direction that we're not checking anything in is the negative z. That's just because we came from there. If we're visiting positive z, the previous node must have been negative z. And we're only ever really unloading positive z from the positive z function if the node is out of bounds. The start direction and the previous direction is rarely met because once again, we're checking that before calling it. But so just quickly here, if we started at this node, we would call visit positive z first. So here visit positive z, passing in 0, 2 as the current node, and we would just go back down, reaching this line again, and noticing we can still visit positive z. So we would call visit positive z once again, passing in 0, 3 as the current node, and then when we're at 0, 3, we would do all of the checks, realize we can't visit positive z because there's no node there. We would try visiting positive x, which we wouldn't be able to because there's no node there. Then we would try unloading positive x, which once again, because there's no positive x, we wouldn't be able to. Same goes for the negative x. There's no node, so we fail. And then finally, we would add current to the list of nodes to load, which in our case would be 0, 3. Then going back in time to when we are still only at this node. So now everything that went up from here is completed. There's nothing else to execute. We're back at this node. We've just called visit positive z and that's finished. And now we check if we can visit positive x. So if we pretend that this is actually the node that the player is in and the start direction was also positive z, then we would check neither start direction nor previous turn is negative x. And we have a positive x node because this 1x2 is here. So we would call visit positive x, passing in our positive x node, the start direction, which remains unchanged, and positive z. So when we call this visit positive x, we're passing 1, 2 and positive z for both the start and the previous turn directions. Then within positive x, we would do all these checks again and keep visiting positive x. As we did before where we went up, we would keep going to the right. So now visiting 2x2. So calling visit positive x a second time, passing in the same directions, which means now our current is no longer 0, 2, it's actually 2x2 with our start direction and previous turn remaining unchanged, both at positive z. Then once again within this new node we check visit positive x, but as we can see there's no longer a positive x node. So now we check if we can visit positive z. Here this is the case because we have this positive z node and neither our start direction nor our previous turn are equal to negative z. So this function would be called, but now we'd be passing in the positive z node. So 2, 3, the start direction, which remains positive z, and we'd be passing in positive x. So now this previous turn becomes positive x, but we're visiting this node from positive z. And because our start direction is positive z and our previous turn is positive x, that means we're no longer able to, from this node, go negative z or negative x because they're the opposite of this start and previous. So once we get to this node, we would firstly check, oh, we can't keep going positive z. Then we check positive x, there's no node there. And then we would check negative x, but because our previous turn is positive x, right here, our previous turn is positive x, this is within visit positive z, this line would fail, so we wouldn't be able to visit it, but because we do have a negative x node, we would try and unload it. So we would call unload negative x, passing in the current node, which is 2, 3, the negative x node of the current node, so 1, 3, and positive z, because we're unloading after going positive z. For the previous turn, negative x is automatically filled because we're unloading negative x. Now we would go through this again and check if it has a negative x node, which right here it doesn't. We would then check if it has a positive z node, which it also doesn't in this case, but then we would check if it has a negative z node, which we know it does. We would then check that at no point previously has positive z been either the start direction or the previous turn. However, we know that when we called this unload negative x, we passed in positive z as the start direction, and then negative x was automatically filled in. So this means that this if statement would once again fail, because here we did go positive z and then started unloading the negative x. So because we went up, we no longer are allowed to go in the negative z direction. So this would once again fail and we'd simply add 1, 3 to the list of nodes to unload. Then we would once again backtrack, everything here is terminated, everything here is terminated, and we would come back to this node, which would now be checking if we can go negative z. We figured that it didn't have a positive x node, we checked for positive z, which it did, and we went through the entire thing. And let me just say quickly, after doing all of this, when we backtrack initially, 2, 3, this node right here, got added to the list of nodes to load, while this node 1, 3 got added to the nodes to unload. But so we visited positive z and did everything we had to do there, and now we will visit negative z. However, at this point we went up and to the right, so our start direction was positive z, which means we cannot actually visit this negative z as it's against positive z, so we would unload negative z, passing in the current, the negative z node, and positive x, with the negative z node automatically filling the previous turn to negative z, and then we would continue trying to unload these nodes. So going down, calling from 2x1, unload, and keep going. However, here it is once again worth mentioning, because we're going unload negative z, so in the negative z direction down, we would only actually call unload positive x if the positive x node is loaded, which means list if we go to the node matrix at that index. We're checking if the node has already been loaded. So that means after getting to this node, so we came unload -z, we would try and unload +x, but if this node was never loaded, then from this unload -z, this unload +x would not be called because the node isn't loaded. So this is another way that we stop it, but at the end we still add it to this list of nodes to unload. So nodes to unload would also include 2, 1. And this basically happens for every single direction. So if, as we were saying, we're starting here, we would only call visit +z with 0x2 and visit +x with 2x0. But based on where the player is, like if we're in this cell, we'd still call +z and +x. So after we get all of the nodes to load and nodes to unload, what we do firstly is we iterate through the entire list of nodes to unload. So here it would be 1, 3 and 2, 1, and we add every single path that leads out from that cell. So what that means is, like when we were getting the first directions to actually go in, so 0, 2 from 1x1, the starting position, we simply add every single node that's adjacent to this cell and is accessible because the wall's been broken. So in the case of 1x3, we would pass 0x2 and 2x1. So they would both get added to the list again. So the list is now 1, 3 to 2, 1, also including 0, 2 and 2, 1, and vice versa for this node. We add 2, 2 and 3, 1, which would look like this. Now you'll see that there's duplicates, but this is once again because we want to make sure that we actually unload everything, and there's just cases where a node might remain loaded even though the player's far away. So this is just kind of making sure that we really get everything that might have been loaded previously that now needs to be unloaded. We then go through every single node on that list and using the node index get the base index of the cell. So this would mean the 1x3 would become 1x2, the base index, 2, 1 would remain because it's a base index, 0, 2 also a base, 2, 1, then 3, 1 and 2, 2 whose base index is also 1, 2. So this list would go to this list, after which we make the list distinct, which makes it into a distinct list, removing copies. So here 2, 1 is repeated, 1, 2 is repeated, and now we just have 1, 2, 2, 1, 0, 2, 3, 1. These are the nodes that we want to unload. After that, we iterate through the entire list of nodes to load. So here briefly, I'll just use 0, 3 and 2, 3. Here I've quickly added 2, 2 because it would have been added to the same list, but it would include 0, 3, 2, 3, 0, 2 as well. Then iterating through the nodes to load, we use the node index to get the base index of the cell that the node is part of. So here for all of these, just the one in the bottom left corner. Then we check if the list of nodes to unload contains the node to load at that index. So here if we're looking at 2, 3, we got 1, 2 as its base index. We check if this list contains 1, 2, which it does here, and if the list of nodes to unload contains that node to load, we remove it. So we basically strike that out. Then here if we got the base index of 0, 3, which is 0, 2, we see, oh, the nodes to load contains that and the nodes to unload contains that, so we remove it from the nodes to unload. So here in our small example, what we actually end up with is 2, 1 and 3, 1. These two. After that, we make the nodes to load distinct again because multiple nodes might have been set to load, but they shared the same base index. And then we just firstly iterate through the list of nodes to unload and call unload cell with that node's index, which is now actually the cell's base index. And unload cell just checks if the node is actually already loaded. If so, then it calls unload cell on the node within that node matrix, which here within cell node is just this function. We once again make sure that the cell isn't already unloaded, which would mean we wouldn't have to unload it. And if it is loaded, then we call unload cell components, which here you can kind of ignore this, but in theory we would call this disable cell function within the cell script, which disables the walls, floors, ceilings, props, and spawn points and sets this bool. Now after unloading all the nodes we needed to, we then do the exact same but calling load cell, which makes sure that the cell isn't already loaded. If it's not already loaded, we call load cell, which is part of the cell node, and here load cell once again make sure that the node isn't already loaded, and within the cell script, load cell just enables the cell, basically doing the exact opposite, enabling the walls, floors, ceilings, props, spawn points, etc. But that's the main function of the load player area. Because we have multiple levels and we want to be able to walk through them without there being a loading screen or some other handoff, we also get the option to update the load player area, which would just be here all the way at the beginning in level manager. After we initialize the load player area, we actually subscribe to an event within the load player area, which is player exited level. This is what's actually called here. So if the player is to the right of the node matrix, basically out of bounds, we call on player exit level. That just unloads all the nodes, iterating through every single node in the node matrix and unloading it and setting that value within the node matrix to null. Set the node matrix to null and then invoke this function, which back on the level manager is right here. We then increase this player level variable that just tracks where the player actually is and can be used to index the list of levels that we created.
make sure that it's not at the end of the level, and then update the load player area, passing in the next level's cell matrix and the level's position within the world into this update load player area, which can then be used to find the level's offset. And it just all restarts basically, clearing the nodes to load and the nodes to unload. Now within the actual editor, what this looks like is if I toggle this use load player area full and I make sure to spawn all the props. Now, unlike before where we just had the whole level, here we just see the wireframes, so this is all the colliders, but the only cells that are actually being loaded are the ones directly visible to the player. So here, this is the entire floor outline. However, as I move around, if we go to the right now, another part of it all gets loaded. If I go forwards and then to the left, the cells below get unloaded. This is just running every frame, and it just means only a small part of the world is actually being included at any given time. I also use this load player area to toggle on or off the spawn points. So as we saw before, these spawn points have this little collider, which right now is hard to see because there's a light that's actually directly above it, but it'll only grab a light from the object pool if this collider is enabled, or else it just won't even notice that the player is overlapping. This means that while the player is near, these spawn points are still enabled. However, if I were to grab this cell, which is unloaded, as you can see, it also has this spawn point, but here, this is what the spawn point looks like. However, the collider is disabled. What this means is, as you can see, it's right here. Even though the player's load area trigger actually encompasses it, so here as I move around, there's no light that's being brought over, because it knows that even though the player might be close enough to it, it's on the other side of a wall and it wouldn't be visible. However, if I get closer to this cell, which leads to it being loaded, right here, now suddenly the spawn point works as expected, and this light has been grabbed from the object pool, alongside this audio source. The same goes for all of the doors. That's why I can get away with so few doors, because even though the level itself is large, this large, only a small part of it is actually loaded at any given time. The purpose of this system is because Unity does have something called Occlusion Culling, which just means when the game is running, if there's a wall, whatever is behind the wall, the computer doesn't try and draw it. It just says there's nothing behind it and it ignores it. However, this occlusion culling only works if the entire world is built out before you press play. So if the whole level was created and then I started play so it wasn't procedurally generated, then I wouldn't have to do any of this because I could bake this occlusion culling data into the map. However, because I'm literally creating everything randomly at runtime, this occlusion culling was never an option, which is why I had to create this system. But if we just look at everything together, so including the paths and the props, right here, you have all of these paths, all of these props, but none of the props are being loaded either. So I can also, I doubt I'll actually talk about this, but you can interact with some of the props. So here I can throw this. There's also, you can push these around and actually just, maybe quickly, but so if I drop this and then I have the mug here, it is considered a prop and it's part of this cell. So if I look at the whole cell, this mug is a prop, but if I, the player, come over and I pick it up, if you look all the way to the left on the editor, when I pick it up, it disappears from that cell, and it basically got given to the player. It's still the exact same mug. But now, if I were to bring it to a new cell, so now you see the cell in which it was actually created is unloaded, the prop itself is still loaded, and if I come over to where the player is, this same mug, when I drop it within this cell, now you'll see it's been given to this new cell. So when I call unload props for this cell, it'll still call it on this new mug, even though it was spawned in a different cell. So it basically got handed over to this cell. This is just so that you can pick stuff up and throw it, and it'll still be used in the occlusion culling kind of thing. But yeah, this is basically the project, just here, running around. It gets loaded, unloaded. And yeah, if I had any feedback for anyone who's trying to do something similar, honestly, it would probably be don't, because procedural generation, this project was a lot of fun to build, and I had a great time creating it, and all these kind of little puzzles that I had to solve. But at the end of the day, it's kind of like creativity without bounds. There's just a massive trade-off between what you can actually create and how much it's actually worth. Here, I essentially create infinite variation of levels and whatever, or near infinite, but it's just boring. It's pure randomness, and so you need to keep adding parameters and make sure that it's still interesting and feels kind of human created, which is the opposite of what procedural generation does. It just kind of spits stuff out. So then you're just trading in kind of quality for just massive quantities, which is great in certain scenarios. Like Minecraft does it great, but Minecraft also just has so many parameters set in place for like creating the biomes and all that. It is still procedurally generated, sure, but it's not random. And here what I built was basically random, but it just doesn't serve. I don't know. Had a lot of fun though. I think this is more of like a programming project than anything. But yeah, big ups. Thank you for watching, and if you have any feedback on the code or stuff, please feel free to leave it in the comments. I'm always open. I know that this is kind of botched. I really started learning C# a couple years ago, barely, in just some programming classes for video games as a minor. So I've just been actually learning it individually or just kind of solo for a year now. It's been fun, but I know that there's definitely some customs where there's probably parts where I do something extremely inefficiently. If you don't have constructive criticism and simply wish to insult me, there are other videos on my channel in which I have my face. So if you're going to do so, please at least try and make it personal. And yeah, I don't know. Maybe you learned something. Maybe not. Maybe I learned something. Maybe it's about the procedural generation we made along the way. Anyway, I am out. Peace.